I like it to be like that, and then
So, good morning. How are we doing today? After the exhausting poster session yesterday, you're fine? So today we have a kind of a Zurich day. So as you might have noticed, I'm Ari Seitzaner, currently working in Paris. But earlier I was in Zurich, and we have a pleasure after the coffee break. We can welcome my former colleague Marcella Januzzi. So we will give the lectures of this morning to Marcella. And I will be talking about methods which are not limited to the QMMM. They are very general, so all the molecular dynamics schemes, be the MM, QM, or the mixed QMMM, the procedures which I will describe, most of them will be applicable for all of them, except of course when we come to the Car-Parrinello dynamics, but you will see this later. So I chose to start with this lecture. They are pretty similar, but there are some material in this first lecture which I will present, which I will use in the second one. And of course, at any point, if you have any questions, please do not hesitate to interrupt me. I've seen you are very active with questions, and I hope it continues this way. So, we will be talking about numerical integration schemes. So these are the way how we proceed, how we implement these molecular dynamic algorithms on the computer. And then I will discuss some of these issues with constant motion, which you have seen already. A new fancy pointer. I will change the mode every now and then to keep you entertained. So, the advantage is you can only read what is in the spotlight, right? So, measuring accuracy and so on. So, which are important parameters, which maybe once at the beginning of the simulation you will check, then you might control them quickly during the simulation. But usually when you choose the parameters well at the beginning, they work well throughout the simulation. And of course, I will be only talking about algorithms related to molecular dynamics. Now I go some very basic molecular dynamics, and sorry for those, maybe most of you who will feel bored, but I thought we have to go through some of the basics, just that we are sure that we all know. So, of course, very basics of molecular dynamics is the Newton's equation of motion. The force is the mass times the acceleration, and the acceleration we get as the second time derivative of the position of the ion. So this tells us the propagation of the atomic trajectories on time. Now our task is to, when we have the atomic positions at some point, how we propagate those. So the forces we can calculate, which I will come later, but it's like in the molecular mechanics, the BFT, it can provide you the forces. So we have what is on the left side, and now it's just a question how we propagate the right hand side to get the trajectory. So the position of all the atoms is a function of time. You have seen many times already, we often talk about with the Lagrangian. So the Lagrangian contains, in this case, the positions, the atoms, and the velocities. So it's not the first time derivative. So the velocity, or you can also talk about the momentum of gas. And the Lagrangian in the simplest case, suppose the kinetic energy of ions minus the potential energy. And the potential energy in MM, you get it from the force field, and QM, you get it from the electron extraction method, usually BFT. And then we have talked 2 days, what do you do when you want to mix them, how you get the potential energy in the mixed QMM. And then you get the equations of motion, you take the full time derivative of the derivative of the Lagrange and the partial derivative of Lagrange with respect to the velocities. On the right hand side we have the position partial derivative of the Lagrange. And the most common algorithm which is used in simulation is the Vela algorithm. There are a few variations. What we'll be using is the so-called velocity Vela algorithm. So, how to discretize this equation? If we write the position of the ions, now let's see if this one is maybe easier. So the position of the ions at the next time step, we can get it using the Taylor expansion, the current positions, delta t times the time derivative of the positions, which is of course the velocity, and then the second time derivative which comes from the acceleration, which is the acceleration, and we have already written that it's the f divided by the m. And this sets the Taylor expansion, the three first terms. Now, then if you evaluate the forces at the next, these new positions are t plus delta t, you can get the forces and then you can update the velocities. And you know everything at the t plus delta t on the right hand side. So again, now you can go to t plus 2 delta t. But this is a very simple velocity. This is actually the normal Vela algorithm. So you can get the propagation behind the positions if you can calculate the forces, because you can get the velocities lost. So this is very simple. That comes from mathematics, from the Taylor expansion of the atomic positions. So the advantage of this algorithm is that it provides very good short-term stability. And the other algorithms, which have maybe better short-term stability, and you might have large time steps with the other algorithms. But what really the big advantage of the velocity Vela algorithm is that it's very simple and efficient. So it's just a few lines in mathematics and a few lines if you implement it, and it's very efficient. So you only need the positions, velocities, and the forces. It's very simple. You also don't need many arrays to store those quantities. And you don't need any high energy derivatives. So we only go to the second term in the Taylor expansion, which is the forces, the acceleration, and acceleration we get by the forces. And it's easy to show that the algorithm is still correct up to the third order in the delta t. That's a step in the Taylor expansion. It's explicitly time reversible. It has been shown that many of the good properties and good propagators come from this. So what it means that if you have a trajectory propagated, if you switch off or switch backwards the velocities, so invert all the velocities, you can propagate backwards and you get in principle to the initial state. Of course, they're not even that one. They were no numerical errors and so on. But in principle, you have this time reversibility. Like I said, it's often very good to have such an algorithm. It's a symplectic, which means that it conserves volume in phase space, which means that it's once started the simulation, it will explore that part of the phase space. It doesn't decrease, it doesn't increase. So for example, that you don't start to sample only one part of the phase space along the trajectory. It remains constant. And it has a very good long-time stability, so which you can see, which we control often with this energy conservation, another conserved quantity. So this is very good in the Vela algorithm. This and the advantages why most of the calculations nowadays in modern dynamics they actually done using the velocity Vela algorithm. So we come to the most important parameter in the velocity value algorithm. That's of course the choice of the time step. How do we choose the time step? Of course, we want to choose it as large as possible, so that we get most of the longest trajectory in the same simulation. So we want to maximize it, but we of course also want that our simulated trajectory is realistic. And what is realistic? So it's this that we get stable dynamics. So we can control that using the energy is conserved, or that there's no, or often there's a drift, but that's acceptable. So I don't know if you're familiar with drift. So usually the conserved quantity is not exactly constant, but it changes a little in a systematic way. And the slope of this change is important. So if it's too large, so if you have a huge drift, probably you will not get a good description of the quantity that you wanted. So there's always some, so now it's just a question, how do we make this drift reasonable? It's up to you to choose when it's reasonable, but it should be done once. Of course, there are some general rules how to choose at that time step, and general, the easiest rule of thumb that the time step should be something like 5 to 10 times smaller than the fastest period in the system, or the fastest period of an oscillation in the system. Most of the time, that's of course hydrogen vibrated against an atom. So that's in the order of tenths of femtosecond, or let's say 10 femtoseconds. So that would limit the time step 1 to femtoseconds. And the smaller you make it, the more accurate you are, the smaller the drift. But again, you want to maximize it to get the longest trajectory possible. In most cases, we will use something like 0.5 femtoseconds, so half a femtosecond, or maybe even a little bit smaller if we are using the light hydrogen. Depends. If you have, for example, the heavy atom hydrogen bonds fixed in many force fields, then you can use a large time step. So if you're doing something fixed water model like tip 3P, 4P, then you can use something like 2 femtoseconds, because biased oscillation is no longer the OH stretching that would be in the flexible force field. There you are limited to something like 0.5, 0.3 femtosecond for capacity. One interesting feature of the velocity delay is that you can change the time step during simulation. So you can, if you realize that okay, maybe I have too small time step, I can take a larger one, or you just want to try it. You can take the current positions, velocities, and propagate it to different time step. So it's continuous, even if you change the time step. It's not done of course often, but it can be done. This is so this is a simple example of the choice of the time step. I took a dimer of aluminum trichloride. So it's a closed shell molecule as such. And they often, the liquid LCl3, they cluster. And then instantaneously you have dimers. So we just took one of these dimers and put that in the vacuum, and then we did the molecular dynamics with different time steps. And in the figure you will see how the choice of the time step affects this free energy, which is now supposed to be our concept quantity. So if we start with a very large time step, that should be the violet line. I think it's violet, I think it's this one of these, and it diverges immediately at the beginning. That's because the time step is too large, and immediately you get divergence because the time step was too large. So we don't have a concept quantity because the time step was chosen too large. Then if you choose a very small thermostat, smallest one here, we get stable dynamics. This is just 45 picoseconds. These one will continue. Then taking something intermediate, well, the blue one is not seen, but I don't know if you are able to see the yellow one, the previous one, even 350 gives stable dynamics up to 25 picoseconds. That's probably continuous. But you see, this example is diverging only after something like 12 picoseconds, 12, 13 picoseconds. So it doesn't need to be instantaneous, the divergence. So usually what one does is indeed every now and then during the simulation, one looks up the constant quantity, whether that's more or less constant or the drift is kind of linear. So that the drift should also not start to increase during the simulation. Because if you continue the simulation, then you will maybe end up in the divergence at some point. What you could do at that point is that you, as I mentioned on the previous slide, you can decrease the time step, and then you should get a smaller drift. Okay, so there's an alternate way of deriving this equation of motion. There's something developed a lot by Mark Beckerman and co-workers in the last 1-2 decades. So they were looking for different integrators, and they started with this form of mathematics with the phase space designed by Gamma. So it contains the positions and the velocities, the commutator, and the Hamilton's and Newton's equation of motion is this one. So then you can define different Lagrangian which fulfills these equations, and then formally you can write this equation that the gamma, the phase space at time t, is the initial phase space propagated with this e to the I and this new Lagrangian with the exponent, complex exponent. So this way you can mathematically derive an integrator. But I don't think that at the end they obtain anything which is comparable to the velocity relay. But for some specific applications, you can derive this mathematical way in integrators. The simplest case, you get the algorithms also this way. But like I said, for some specific cases, you might want to use new integrators. This is one way of putting them. So then there are some tricks which I will mention very shortly. You have already done the first day. You were using the first list, simulate annealing. If you remember, Carmen told you that you will scale at each step the velocities by 0.1%. So we multiplied the velocities at each time step with 0.999. That is simulated annealing. You can show that this is the same as exponentially the average temperature goes down in simulation, because you are taking kinetic energy at each step, but slowly. So exponentially the temperature comes down, and this is of course what nature often does. Something is hot, it cools down exponentially. So this simulated annealing is a way to kind of mimic the optimization algorithms in nature. And simulated annealing, as also Gamma mentioned, if you have many degrees of freedom, so thousands, tens of thousands of coordinates, this uses a very good algorithm to optimize. Instead of using the normal optimizers, the number of degrees of freedom is so big that uses the simulated annealing is better. The other advantage is that you might even get awesome local barriers, so you get closer, necessary to the global minimum of the system, but you are kind of you have more chances of getting small barriers instead of the minimizers might get to the local minimum. Yeah.
You see, if you start estimating the annealing with a high temperature, you start with 300.
Yeah.
Yeah. So the comments starting with like 500 Kelvin.
Yeah. So it depends. Of course, it also depends how stable your system is. So that you don't break any bonds. So you shouldn't start too high. And in some cases, like glasses or so, one can start from thousands of kelvins, where the system is stable, the bonds no break. I mean, for example, that you don't dissociate water.
And doesn't it always lead to a global minimum in the end?
Well, it should, but it's still, you should have an infinitely small cooling rate. Only then, I don't know even if then you are guaranteed to be at the global minimum. I mean, you should be sure that if you start at some part of the phase space, then the temperature initially is so high that you get all this barrier. If the temperature is lower than this barrier, you still be that you don't reach it. Like I said, you should start with a very high temperature, but if you start to dissociate your molecules and so on, it's too high. So there's no guarantee that you get to the global minimum. But with the simulated annealing, like I said, if this initial temperature is higher than this, you have a probability of getting toward the global minimum. Of course, it could be that you come also back. So that doing the simulated annealing, you get back to this local minimum. But well, it's just that the probability of staying here is large because the system knows inherently the energy flow. So most of the time the system will be on this side, even if the temperature is high. And then the hope is that when you cool down, you get trapped at the global minimum. Like I said, there's no guarantee that you will get to the global minimum. Yeah.
I have a question about the time step. You said that it's possible to change the time step during it. You know there are these adaptive time step. How do they predict whether you have to increase or?
I don't know those, but I guess it has to go somehow. Either they calculate the highest frequency of the flight, or that they look at the observation. But I'm not familiar with those. Any other questions? This one? Let's change the slide. So then, just mentioning, you can have multiple batch algorithms. One of them is about the RESPA. So this means that some system, a part of the system is propagated with different time steps as the other one. This doesn't sound very intuitive at the beginning, but it could be that you have some very slow degrees of freedom, like the macroscopic structure in your the large-scale structure in your system. And you know how to integrate those degrees of freedom separated from the slow ones. What we are doing actually is we are using multiple time steps in kind of corrective scheme. So we propagate the system with high accuracy forces, and then we calculate with lower accuracy methods the system with small time step. And then we correct again every 5 steps. We correct the forces with another method. So this way we have calculated the computation heavy method only every 5 time steps. It's kind of a local correction which we then improve every 5 steps. So this is another occurrence of how to use the multiple time steps. So we save almost a factor of 5 in the computation time, and be almost as accurate if we use the more accurate method at each time step. Well, of course, then there's the, yeah?
Sorry, the question, can this method, multiple time scales, be used for example for a system that has multiple phases? For example, a solid phase and a liquid. So the liquid is jumping around, but the solid is quite stable. Is it applicable?
In principle, you could use that. You just should be careful that the time step which you use for the solid is also small enough for the highest moments of the vibration in solid. But if you have a very rigid solid which has very low frequencies, then you could use some of these algorithms. If you have clear separation of 2 phases or so, or very fastly oscillating liquids combined with very slowly vibrating, then you would have 2 different types for the fast degrees of motion. slow ones.
For example, for the core, planes of the solid shall not.
Well, still you have the highest frequency components, so that's limiting almost the highest oscillation even in the solid. But if that's much slower, for example, you have OH bonds in the liquid, and just heavy atoms oscillating against each other, maybe you have indeed a difference of 5, 10 in the frequencies, the highest frequency of the OH, and the vibration solid. Then it would make sense to try to use this kind of steels. So Car-Parrinello organisms, I think you are all familiar with this, and you mentioned it's just at the beginning of the simulation. This was something new, and of course nowadays we can afford much bigger systems. At the beginning, they were using sometimes 64 atoms of neon. The box was very, very small. Now you have seen the boxes much, much bigger. But in most of the simulations, we are using Car-Parrinello organisms. For example, if you solve something in the realistic system, we have lots of water, and that's better described if you have the water periodic. So your system is periodic, but you have enough water that it kind of isolates the solutes from each other. So most of the simulations are. It's not compulsory. The eval summation, well, I don't go into details here, so that's just something if you have charges in your system, one has to take that into account during the simulation, and you want to do that efficiently, so the eval summation was the first method which allowed to use periodic systems and charges. Now there are variations like the particle mesh eval and so on. Particle mesh eval, SPME, which are already implemented methods. Then thermodynamic integration, so you will hear something about the other methods. Cell lists and so on, they are just numerical issues, how to speed up the calculations. Now it is that you have maybe hundreds of thousands of atoms, it's indeed completely different than the old days when you had tens of atoms. So to make the codes more efficient, then there are more and more numerical tricks. So some codes are faster in small systems, but other codes might be faster on the other bigger systems, or some codes they are more, or they are faster on parallel computers. In the QMMM case, it's always the DFT, or let's say almost always it's the DFT or the electron structure part, the QM part, which dominates the computing part. So the MM part is not that important. And then the QM part, you have these tens, hundreds of atoms. So these issues are not that important. It's more for the MM part. So, small summary for the molecular dynamics. You can do the real dynamics, so Newton's equation of motion, and the maximum time step where I put 1 femtosecond, that we need the OH. If you have light hydrogen, you get down to something like 0.3, 0.5. And we will later in the morning we will discuss the different ensembles, how to treat the constraint temperature, then the constraints, well, restrictions of the atoms. We have already discussed this, so for some distances, animals, and so on. This is something which has been discussed. We are not going to the algorithms because you need specific algorithms. For example, to build the algorithm, you have different equations for the constraints than other integrators. So the method how you implement the constraints are different with the different integrators, but like I said, we are not going into details. And then I will come to application molecular dynamics. Do you have any questions on the general part? Yeah.
So to quantify this, I'm not really sure how to quantify that, because it depends on the size of the system, the time you want to run it, and at which point is it a problem for the observer that you really care about. Because if you take Lomax, for example, and you do a like standard, as they say, you have at least that to input, but I don't know if how was just not used to it, but since it was from the defaults that come from the, and I was doing things as standards, so well maybe this is just what you can accept, so I don't know how to practice that.
Well, of course, it depends always on the system, what you can accept, and as you say, it depends on the observables. If you are interested in some reaction barriers, which change just by some few kilocalories per mole, and your conserved quantity of this drift is much, much bigger. So if you simulate, let's say 1 nanosecond, and your system changes, if you convert that into temperature to drift, if it's tens of kelvins or tens of degrees, and you have barriers which are just few kilocalories, it's much bigger. So if you're looking for something very small, so small barriers, so then the drift of course should be small. But then it depends. If you are only interested in, let's say, the average structure of the liquid or the average structure of your solvent around your solute, then that it doesn't matter so much because you get the average structure. The reactions are of course much more sensitive, also because it's a single. But so there's no general rule. It really depends. So what I would normally do is to look indeed the drift. Then I have to know more or less how long I want to simulate. And then because it's a linear drift usually, I can extrapolate how large energy change would be. And then indeed we can, if we are doing NPE, so we don't control the temperature, it could be that the system changes the temperature tens of degrees during simulation. So that's one of the reasons why later we will discuss the NDT. So we control the temperature at the average, it's this constant.
Yeah, like I always look at even if I have at least the total, the temperature and the total potential.
Yeah, exactly.
That's really the problem is when you have the list of that you challenge.
Yeah. I mean, again, if you are looking at something, a reaction and barrier, even a small change might be important, but the thermostats will forgive you a lot because it keeps the average temperature where you want. So it helps with the drift. There might be some drift, but at least the temperature is not increasing. And if you control the internal potential energy, that's another. Okay, so next I will go quite quick, definition of molecular dynamics, because it has been already discussed before. So two methods, Car-Parrinello method versus the Bohr-Oppenheimer. So I think I can go pretty fast because it was covered already. So the Newton's equation of motion again, then just shown, the forces are shown as the negative of the derivative of the total energy with respect to the atomic position. So this is just the derivative of the energy, also can be written this way. So how can we get this in different methods? Force fields it's easy because the energy is analytic. In DFT, especially if we are using plane waves, the derivative is actually very easy to calculate also. So the expression for this derivative is easy. So we get the forces easily. So there's not much difference between the so-called classical molecular dynamics and definition molecular dynamics at this level. And well, this I don't need to go through motivation why we want to calculate the electron structure or QMM molecular dynamics. You have heard, you can imagine easily. So Bohr-Oppenheimer molecular dynamics, this has been again discussed many times. This is the same as what you do in a classical molecular dynamics. Just I will quickly say a few differences. So I will skip this. This is just how to get the Bohr-Oppenheimer approximation of how to derive it. Just to mention one of the experts in the non-adiabatic dynamics. So going beyond Bohr-Oppenheimer dynamics is Sarah Vanilla, the vice director of Zika. I haven't seen her doing this test, but she's very active in the field of going beyond the Bohr-Oppenheimer approximation. And most of the time we can rely on that. It depends again on your system, but as you probably know, most of the simulations nowadays we rely on the Bohr-Oppenheimer approximation, even if you do DFT. So the Lagrangian, you have seen it, now I've written it once again in the form where the potential energy is written with the DFT, or the most common form of DFT, Kornheim energy. So that's the energy, the Kornheim expression of the energy, which includes the Kornheim orbitals, this psi I, and one minimizes the total energy, the Kornheim energy, with respect to these orbitals, each in d time step. This idea you have seen many times. Just to repeat this to remind you that the Born-Optimum molecular dynamics, we have to go to this so-called self-consistent solution, or the minimum of the Kornheim energy with respect to orbitals at each time step. The coincident motions, which you have seen, is just then there the derivative of the Kornheim energy, and this is, like I said, easy to calculate in the plane wave base set. In other codes, the atomic codes with basis sets which are centered in atoms, we usually have the expressions also the forces, so they can be calculated accurately. It's just that there are a couple of more terms in the expression for the forces, but they can be calculated. So what we needed was this one, and it was mentioned that we want to keep the orbitals orthonormal during simulation. So one way is to use the computation of the Lagrangian multipliers, so that each time that these orbitals, two orbitals of different I and j, they will remain orthonormal. And then we get the expression for the forces, and this is the final expression. In the plane waves, this last term also vanishes. We are doing the Born-Optimum dynamics. Sorry that I go very quick, but I said you have seen most of this already. Now, the big difference between the classical molecular dynamics, molecular mechanics, and the QM molecular dynamics is the self-consistency, or the minimization. So we never go exactly the minimum. That will take, of course, infinite amount of time because we're optimizing all these wave functions. So we always have to set the limit when we stop optimizing those orbitals. And this is depends on the code, how that is implemented. But the closer you go to the self-consistency, the smaller the error in the forces. I guess this is obvious. So if you go very, very close to the optimum of the Kornheim energy, the error in the forces, so the self-consistency error is larger, but you needed more time because you need more iterations. So you had to find, again, an optimum. The idea to allow large error in the forces, so you need less self-consistent steps, you need less computing time, but then you have a large error in the forces. And this error is always beyond the error of the classical molecular dynamics. Because this comes only from the self-consistency. In the classical molecular dynamics, or MM, you have the error from the machine precision of the machine precision is finite. So even if you have an analytic expression, at some point you get to the limit of machine precision. So you say this is now 64 bits for the mathematical operations. But this is basically always larger than that. The error in the self-consistency in DFT or the other electron extraction methods. And this plot is just to show. So here you have the largest element of the electron gradient. So that's kind of to measure how well you are converged. When you go to the more you go to the left, so these are exponential numbers, so it's 10 to minus 14 here. The more you go to the left, the more accurate you are. So the more self-consistent iterations you need to get these small electron gradients. But of course the force is also smaller. Or sorry, the error in the force is here. So again, it also goes down. So basically there's that 3 examples here, you calculate examples. So this line is the result of the test. So it just shows the smaller the error, the more steps you take, the smaller the error in the forces. And now you have to choose the optimum So this was written, this is standard convergence, so this is, for example, the default DFT package when you do the dynamics. Then you can improve that. Then here you get the energy, or the limit of the energy the machine presses. And then you have to go even smaller if you want the forces to be correct. Just to mention the quantities like stress tensor and so on, they converge even slower than the energy or the forces. So the higher the derivative, like pressure is the second derivative of the energy with respect to the lattice vectors, the more accurate you have to be, have the same average accuracy in that gradient. So the energy converges quite fast, but you need more iterations to get the very well converged forces. And like I said, if you want something like the pressure tensor or phonon frequencies using the so-called Parkinson spacing theory, the more you have to go to this left this right. But again, the computation time always increases because you need more and more iterations. So just some notes. So the energy needs to be minimal, of course, because we are optimizing the Car-Parrinello energy. And again, I keep repeating, the accuracy of the forces depends on the self-consistency. And again, this is a parameter which is additional to all the parameters which you had in the classical molecular dynamics. These are almost, without the details what the DFT was, but this is one which controls the quality of the molecular dynamics simulation. And, well, constant motion, I will discuss later. The Car-Parrinello method, has been shown a couple of times. So that's an alternative method to the one-of-one dynamics. And you have seen this expression already. So that's the Car-Parrinello Lagrangian. It depends on the orbitals, the time derivatives, and in the same way as the atomic positions and day derivatives. So Lagrangian contains fixtures, just kind of artificial kinetic energy of the electrons, which is not non-physical. You could have derived a similar equation, but the mu is chosen so that we are not describing the real dynamics. So we call this the fixtures, so now this may be more fashionable to call them fake dynamics of the electrons. And that's rate of these changes in the fixtures. Kinetic energy of the electrons is controlled by this mu parameter. This is all repetition, so I will not go into details. You can derive the equations of motion. You get one equation for the electron orbitals, which looks like one for the ions, but it contains the mu instead of the physical mass of the ions. And then you have the derivative of the quantum energy with respect to the orbitals. So, just to remind you, the main idea of the Car-Parrinello was to do simultaneous dynamics of the electrons and the ions. So, like you saw in this equation, these are propagated at the same time. And the advantage was that we don't need to go to the self-consistency at this time step. So we just use a velocity value also for the electrons. So also this equation. So we don't need to minimize this term, the quantum energy with respect to orbitals. So that's the advantage of Car-Parrinello methods. We don't need to go to self-consistency at its time step of the dynamics. And the constant of motion, as we mentioned, so it's the physical constant of motion, so the potential energy plus the kinetic energy of the ions. But now we have these pictures as kinetic energy of the electrons. So this should be a constant of motion, so this we control, that this remains a constant through the simulation. And how do you know that we have good physical description of the system? So of course that we have some oscillations. We will not go into details, but of course we have some oscillations in this one, because this is the constant quantity. So the sum of these two is constant, so this will also fluctuate. But the fluctuations of these are limited. So it should not increase during the simulation, which of course also means that this remains limited. It oscillates, but it remains limited. If this increases and this stays constant, so this of course has to decrease because of the motion. So this is the way how to control is the quality is to look that the physical quantity does not change, or that we look that the pictures kinetic energy doesn't increase. So let's just show you examples. So this is a way, there were some examples how to analyze the Car-Parrinello method. I will have them also later on the slides, but I will skip them because they will show to save some time. It's just to show you how to make sure that this Car-Parrinello method works. So this is so-called adiabatic separation. So this is one system, a simple system where we have the highest frequency, which is now in terahertz. So we have some terahertz, and some terahertz we have the highest frequency of the ionic motion, to be the highest vibration for some OH system. So that's the triangle. And then this spectrum, that's the power spectrum of the electrons. So then we take the time derivative of the octals and the autocorrelation function, then we Fourier transform that. So that gives you an idea of how the electrons vibrate during the Car-Parrinello dynamics. And so then this height just describes how many vibrations there are at that frequency. But the frequencies are given with these vertical lines here. And the most important thing in the Car-Parrinello method is this adiabatic separation, which means that the lowest of the electronic vibration here is much higher than the highest ionic frequency. So this is the same idea that Mauro was showing, that you stay slightly above the Born-Oppenheim surface and you average just above the Born-Oppenheim. So that's the same as the highest frequency, the lowest frequency, the electrons, is high enough that it averages out before the ions move significantly. This is the idea why the Car-Parrinello method works. So you have the electronic features as motion, and that's fast enough that it doesn't change significantly at the time scale of the ions, but the average is out. I will go through then. This is just early demonstration that you get the same forces in solid silicon using either the Born-Oppenheim dynamics or Car-Parrinello dynamics. This is the difference. So these are the forces, force in the x direction of one atom, and this is the difference using the two methods, so Car-Parrinello minus whatever the forces. And this is 4 degrees of magnitude, 3 degrees of magnitude, smaller than the real force. So the error due to these pictures as motion is small. That remains limited. That's important. So these are some expressions how to estimate how you can, how you should define the parameter mu. I will not go into detail. Just to show them some cases where the Car-Parrinello method doesn't work as such. This is a case of vacancy in a box of, actually then it's 63 atoms of silicon. So that's a liquid silicon. And you see the Kf, the left, this is this curve, that's the fixed uses kinetic energy of the electrons. And it's increasing along the simulation time. But again, it should not happen, but it should remain limited. And you see also that because this increases, the potential energy slowly goes down.
Here, the problem is the system size is small or the time scale of your presentation?
No, it's the electronic structure now.
Sorry.
So it's because the vacancy, just what they describe. So this is the electronic structure of silicon. So this would be the bulk, the band structure. This would be the tape. So in the liquid, you have some discrete energy levels. But the vacancy, that forms energy levels in band gap. If this was the gap in the liquid, when you create defect, you create you put some electrons into the gap in this defect state. And then the problem is that the distance between two levels is so small that when doing the dynamics, this orbital might come very close to this level. And then there's kind of mixing of the two orbitals. One of them is occupied initially and the other one not. And then you start to get into the problem that in the quantity which was shown before. So here, so the quantity which was shown. So this is how to calculate this power spectrum here. So the Fourier transform of the velocities. So if you start to mix the occupied and unoccupied ones, then you start to get frequencies from shifts between these orbitals. The electrons are jumping from one orbital to the other, and that's then a very low frequency here. It doesn't do very fast dynamics. So that's the case also in the liquid silicon. So the band gap, because I didn't have time to discuss it here, so the band gap limits the frequencies of the six uses oscillations. The smaller the band gap, the smaller the lowest frequency, and this box, it means smaller band gap, the lower it becomes. And then if you start to overlap the two frequencies, then it means also, in other words, it means that the electrons start to follow the ions, because the frequencies start to overlap. So the electrons start to be, or some electrons or other two electrons start to be so slow that they start to follow the ionic motion. And then you are lost, because the idea of Car-Parrinello dynamics was to oscillate much faster with the electrons, so that you average out this error in the from the bottom parent surface to the Car-Parrinello. So this was one of the examples, the liquid silicon. Then another one is a simple dimer of tin, and here one sees indeed that HOMO and LUMO in the optimal dimer, they are all very close. When you start to do the dynamics, they start to swap. So you see this increase in the features here.
It's not possible to minimize every n steps to get again the surface Car-Parrinello.
Yeah, but then you are destroying kind of these dynamics. You are quenching the electrons every now and then.
Yeah.
So you're kind of destroying the real Car-Parrinello equation in motion. You had the equation in motion, but now you quench it now and then. So you're kind of artificially changing the system. Well, just what I want to show next is how to go beyond this. One way is to put the thermostat of the electrons. This was mentioned by Mauro. So you limit, take one example. So, sorry. So for example, in this case, this is the pictures is given the energy of the electrons. So you put the thermostat so that this oscillation should not increase too much. So you put the thermostat which keeps the electrons not exactly, but the fluctuations remain small. So if you manage to put that kind of thermostat, then again you are back to you have a constant quantity. Because you have the thermostat, I will quickly show it afterwards. You can propagate the equation in motion. Quench, you're kind of destroying the dynamics, continuity of the, or you kind of take the moment of the electrons every now and then, and that leads to unphysical dynamics.
Is there physical something like how you will put your temperature range so that you control this kind of radiation?
So the thermostat of the electrons.
Yes, yes.
Yeah. So you try to keep them cold, because this kind of temperature of the electrons means how far of the Car-Parrinello surface the electrons oscillate. Again, that's the the picture of Mauro, you had this kind of valley, and this was the kind of the propagation of the, so if the time is just a 1 degree freedom. So if the time goes this way, the idea of Car-Parrinello that you oscillate just above the Oppenheimer surface. And the distance between the Car-Parrinello surface and the true Oppenheimer surface is just kinetic energy, or it's the temperature. And talk it as the temperature. So in these units you say that okay, the electrons are much colder. The idea, again, if they are too warm, the electrons, you start to have the lowest frequency of the electrons. That's again the overlap with the fastest frequency of the ions. Other questions at this point? So just was the algorithm of Car-Parrinello. So you put thermostat, this was showing that as a function of this target, the temperature of the electrons, which is this electron. So what is the heat transfer between the electrons and ions? So there's a kind of optimum there. And this is showing in the case of molten aluminum, which is metal. So this is a real metal, so it instantaneously drift away, or the electrons drift further away from the Oppenheimer surface. And if you use a thermostat, you can just an early example of this. And then they showed that okay, physically, if you do Oppenheimer copper, and you get the same. If you use copper and thermostat, you get the same average structure. Okay, I think I will just quickly remind you of the differences between Oppenheimer and Car-Parrinello, and then I go a little bit into the thermostat. So, hope this is still readable, even though the text is quite small. So, Oppenheimer surface, you always, as the name says, at these times that you go exactly within the error of the self-consistency, you optimize the Kohn-Sham energy if you're using GFT. You optimize the Kohn-Sham energy to some level of self-consistency. But in the Car-Parrinello, you don't do that optimization. So you do only one step to get the forces. Whereas here, in the Oppenheimer, you need to do several steps of self-consistency before you can calculate the forces. So in that respect, Car-Parrinello is faster, but in Car-Parrinello, you have to have this electronic decrease integrated faster in the equation of motion, because you want that on the average, the electrons have already oscillated when the ions move. Or in other words, the fastest ionic velocity is still slower than the slowest electronic decrease. That's why you need the delta t time step, the integration, smaller when you do Car-Parrinello dynamics. So here you have the expensive minimization of the Kohn-Sham energy. Here you only do the autonomization at no self-consistence, only one step to calculate the forces. One advantage for Car-Parrinello is that you get this drift to the self-consistency, or limited self-consistency in the Oppenheimer. Whereas you have, particularly if you use the thermostat and the electrons, you get stable dynamics. In most cases, many cases, we can achieve stable dynamics with Car-Parrinello method, but you have this drift in Oppenheimer. And again, it's an additional error because of the limited self-consistency. So it's not this finite time step, it's because you are never exactly at the Oppenheimer surface due to this in a complete self-consistency. Oppenheimer is easier. You usually have more or less the same machinery, the same algorithms in systems with the band gap or without the band gap. Of course, in cases like CP2K, there are different algorithms you have to use in the case of metals. Whereas then in Car-Parrinello, you can try thermostating the electrons. And as such, Car-Parrinello without the thermostat doesn't work. And initially the Car-Parrinello was used more in the real dynamic systems, so liquids and so on, whereas the monochrome was more used in the solids, like the phonos and so on, doing the MD, more in the solid state community. Now it's much more mixed. Most of the applications nowadays they are using the monochrome. Questions, comments at this point? No? So then I think I'll switch quickly to the other topic we wanted to show you this morning, the different ensembles. Again, I expect that most of you are probably already familiar. Very simple, everyone has heard many times thermostat. So that's the way how to go nowadays when we want to do use different ensembles, especially the canonical ensemble. You probably know the difference. So the easiest ensemble to calculate in molecular dynamics are the MBE. So you have the number of particles, the volume, and the total energy constant. Or to put it that way, the total energy should be constant, except for this three. Then NVT, or the canonical ensemble, it's more physical because you have something like a heat bath around your real system, which keeps the average temperature constant. So even if you put something isolated in the box, liquid in the box, slowly you have this heat transfer. So if it's kept in a room, so slowly the system averages to the room temperature. While the slow heat transfer through the walls of the box where you keep your sample. So that's more physical than MBT. And then MBT, where you have constant pressure, this you can also do easily with molecular dynamics. In the QM world, if you need to change the box of the QM, usually you need to work a little bit harder to implement it. It's possible. The both code CKME and CP2K, they can do MPT dynamics. In the QM, MM, usually we keep the QM box fixed. It's not so important here, but in principle, you could use the box of the QM region also variable. In the cases, most of the cases, we keep that fixed. And then, of course, the tri-canonical ensemble where you can even vary the number of particles. This starts to be much more complicated. In molecular dynamics, it's very difficult because to make a particle disappear or appear in the system, it usually leads to discontinuities, right? Because how do you suddenly start to propagate a particle which wasn't there before? So in Monte Carlo, it's easy. You have these steps. Monte Carlo steps where you make a particle disappear or appear in your simulation. It's much easier, but in molecular dynamics, it's very, very rare to have a canonical ensemble. It's much more difficult. So the three first ones are kind of standard nowadays. The microcanonical, MBE, so it's just a different way of writing that. The total energy of the system in the QM simulation is that you put mechanical energy, in this case I have written with the Hamiltonian, plus the Hamiltonian, plus this interface, the QMMM interface, these mixing terms between the QMMM and particles. When you sum up those three, then this should be constant motion. And usually you have some fluctuations to these numerics, the finite time set and so on, finite machine processor. But that's usually the fifth digit, so it's in the maybe total 8th, 9th digit, and this should fluctuate because they can be increased, but again it should be small. What is small depends on your system and what you want to see. I just repeat. I quickly show the derivation of the Galilei algorithm. It was via the Taylor expansion of the atomic positions at time t, plus minus the Taylor expansion, you sum up, and you get to the Galilei algorithm. And then using the QMMM method, you have to take also account these interaction between the QMMM and it's a bit more involved than if you're doing purely QM or MM. You also have to take into account these terms when you calculate forces. But it's doable, it has been implemented. But this is just the derivation equations. So just to remind you that at the beginning, even if when we do in the equilibration, there can be some jumps at the beginning, but after that you should have the constant of motion, at least the total energy in the system, which after the very few steps at the beginning, the total energy is almost constant. You see a small drop, but there's a small drift. Otherwise it's like a straight line, even if the temperature in the system fluctuates. The current example is just a way to go into this more realistic case, so we can control also the temperature. So the question was, if we have the total kinetic energy of the ions, which we on the total of this, on the average, it gives you this temperature, the average temperature of the system. To remind you, in most of the simulations, in realistic simulations, we never have exactly the temperature as a constant. It's constant only on the average. It always fluctuates. The bigger the system, the smaller the fluctuations. In the MD world, you will never see a case where the temperature is really constant, unless you use an equation of motion, which keeps the energy as constant. So what we talk about, we don't take this time derivative, what we talk about the instantaneous temperature. Again, it will fluctuate. Now the question is just how can we, on the long time scale, on the average, how can we adjust the velocities so that we have the average temperature fluctuating around the constant. And the idea comes from the heat reservoir, again, like I mentioned in the example of the room temperature. So we have this gas around. So that's a huge reservoir of kinetic energy for temperature. So on the long time scale, the system, your real system you are interested in, will equilibrate with the temperature of the surrounding, or this heat. And in this case, infinitely many degrees of freedom, or the number of gas molecules in this room, for example, it's almost infinite on our scale of ME with hundreds of thousands of million particles. So how to achieve this kind of heat reservoir? Well, the most used algorithm nowadays is this Numerical method. So we add 1 degree or few degrees of freedom, which kind of mimic this ensemble or the surrounding. And the idea of how that's done is that we will change the velocities of the system, but not. I will already show you the whole Hamiltonian, not in the way of rescaling directly the instantaneous velocities, but adding these degrees of freedom. And here it's written with the S. So that comes addition, so this gives additional terms to the total Hamiltonian now. So we have the atomic velocities, or the ionic velocities, now scaled with S. So we can imagine S is probably quite close to 1, so we don't disturb the system too much. Then we have potential energy. Then we have these new terms. So the first one looks like kinetic energy, so it resembles the ionic kinetic energy, but the degree of freedom is this S, which comes from the thermostat, and the time derivative now, so this is like a kinetic energy. The Q is like a mass, we'll come into that soon. And then you have this kind of term, which is the potential energy due to the thermostat. So again, we add to the Hamiltonian, put that the Lagrangian, the same thing, the kinetic energy term and the potential term. And the idea of this new degree of freedom is that when the system is colder than what you want, it will pump energy in your system. So kinetic energy to the ions, using this S factor here. And when your system or the instantaneous temperature is higher than what you want, then it will take some kinetic energy, so the S will be slightly smaller. And again, the idea is that you don't change too much at the time scale of the atomic vibrations, but that the average temperature on the time scale of several oscillations of the ionic system remains constant. It's not a good idea to try to change the temperature at the time scale of the vibrations, because then you are directly modifying the vibrations. But you try to modify them slowly, so that even if you have fluctuations, the system keeps coming back to the wanted temperature. And that time scale is controlled by this parameter Q, which is kind of like a mass. It's a mass for this degree of freedom of S. The larger it is, the slower this response to the deviation of your instantaneous temperature to the the slower the average temperature approaches the wanted value, and the smaller it is, the faster is this change. Any questions at this point? So what is actually used in reality? So okay, this is just what comes out of when you take the Hamiltonian, the equation of motion. So you have this scaling factor of S. It's close to 1. And so this term is like the friction term. So that will, together with the S scaling with the forces, that changes the average temperature on your simulations. So it affects slightly the decrease of freedom, propagation of the ion, but hopefully not much physically, only at a long time scale. And yeah, there are two parameters: the target temperature, which is in most cases it's something like 300 Kelvin, the room temperature, and the second one is this mass. It's usually given, maybe not as mass, but you can convert that into time scale and so on. And I will just mention these different things in QMML. What you could do, what we tried to do yesterday, I think it was, I think I took out the slide. One way, what we tried to do yesterday, or what was mentioned that you could have done yesterday, is to freeze the solvent molecules initially and optimize only the solute or the QM region first. And then when that is equilibrated, then you start to do dynamics in the full system. This is what you can do. You can have even two different, so in that case the temperature of the MM region was 0, but what you could do, which is easy to do, is that you have different temperatures in the two subsets of the coordinates. So you can have how many thermostats you want, so you can have part of the system at different temperatures as the other one. There are some cases where you even thermostat each degree of freedom in your system. So then you put the thermostat in each Cartesian coordinate, not only the whole Hamiltonian, 1 degree of freedom. But there are many ways how you can treat the Hamiltonians. These are implemented in CKD and CK2K both. And what I will mention maybe shortly. Yeah, here means the same. Just if you implement the Car-Parrinello scheme, so you put the thermostat on the electrons, it's the same basically. You get some extra terms also in the equation for the electrons. And what I wanted to mention, well, you can do the same also for the, if you are doing NPT, you can put an extra degree of freedom for the cell, so you're going MB, also on the cell for the NPT ensemble. Then there are different algorithms, especially this CSVR, developed by Parrinello, Hussein, Benadio, co-workers over the years. I'm not sure whether this is simple. I mean, I guess it's simple and also in CPME, at least it's in CP2K. So that's kind of a stochastic integrated or thermostat. You get the canonical distribution. And this is what many people now use for the thermalization or equilibration of the system. Here you can use a very small time step also. It's unphysical, but this way you can equilibrate the system faster. Just as an example, what I want to mention is that I've mentioned that we put 1 degree of freedom into the system in the no-save-home thermostat. Actually, what is done, for some reasons which I don't have time to go into, is that you put several degrees of freedom. In this case, we will come to that, it will be 4. This is the so-called no-save-over chain. You put the thermostat directly on the kinetic energy of the ions, but then you put the thermostat on the thermostat. And then on the second thermostat, you put another thermostat. So this way it gets a bit more complicated, this thermostating, but it has been shown that it gives you better description of the system. And it's a standard. You need to, if you want to have the equations, you can derive them. That it has been shown that this improves some pathological cases of the initial no-save-over thermostat, like the base phase is reserved when you use the thermostat chains. And, often, one uses a chain length of 4. But this is what one who puts in the input. I think this is in the CPME section or ion section. I think it's in, I'm not sure, but it's in the input. So this is the format for CPME. So this would be that for the ions, the nuclear degrees of freedom, the average temperature should be 300 Kelvin. And this is so-called mass, but now it's given as frequency. So the frequency of the thermostat is kind of 200 wave numbers. So this is in the, not the highest frequencies oscillation system, but somewhat lower. So this means that it doesn't reflect instantaneously the deviations of the instantaneous temperature from the full temperature, but it affects the average temperature a bit slower. So again, it's a bit confusing. This is Kelvin and this is wave numbers. For the electrons, so now we use 0.3, I think this is R3, and units, and then the kind of mass of the electrons. This is just an example of how the format is. And then these parameters, so it's for the chain of 4 of the ions, chain of 4 on the electrons, and then some other parameters controlling the integration of the parts of the equation of motion. And even if we haven't gone into CP2K, I just quickly flash. This will be what you will learn after the coffee break and in the terminal session today how to use CP2K. Just to show you that we have a no-save-over thermostat. Again, it's a chain, the length is 4, and other parameters. And there's also this CSVR. Other kind of thermostat. Now the no-save-over is activated. We could also shift this. This was very quickly introducing the main ideas of thermostating or how to treat canonical systems. Any questions at this point? Everything clear? Okay. I tried to be a bit short, and I apologize if I was too short. But you had already heard the main things, the main difference between the Car-Parrinello and the Bonaparte dynamics. One thing which I'm not sure it was discussed. So whether to use Car-Parrinello dynamics or Bonaparte dynamics, it doesn't make a big difference nowadays. Codes like CP2K and in particular the quick-step code which is used for the DFG, you use CP2K for DFG Bonaparte dynamics. There's no Car-Parrinello algorithm. It's not just that the corner panel would be better, just for convenience, and because the Car-Parrinello is most advantage in the plane wave methods. And I have heard that these months, maybe they will finally implement the plane wave method in CPTK. Now it uses the Gaussian basis at Numerical, so the orbitals, and there probably the Car-Parrinello doesn't bring that much due to the details of the and the computing time of the different turns. But in plane waves, if you have a large bandgap system, like let's say water or some organic molecules in water, you have large bandgap between the occupied and unoccupied states. At the end, it doesn't make a big difference. We saw in the summary, the Car-Parrinello, the time step is smaller, but we don't need the self-consistency. So they more or less you cancel each other, and the efficiency is more or less the same between the then it doesn't make a big difference. What you gain with Car-Parrinello was this better kind of conservation of the better stability. So the drifts you can control with the thermostats easier than before. It doesn't make a big difference. Now we'll run away. We went to check if we can have already coffee break. No questions, no comments. If not, then let's hope we get the coffee, and then afterwards we have Marcella introducing you to CP2K work. Okay.
I just want to say your solid and solvent, for instance, or with another solid, interaction. You should benchmark them with like we produce without the dissolution function. But then one of them is because for instance you can assume that does this not dissociate? No, I don't.
Yes, probably will
potential goes down. Complex, and you have anything in the middle, and then the other way is the IDOH groups from the water dissociation.
Retarded version of breakfast.
Just directly distance.
Vale, pero el comando mandado es igual. Exacto.
The charge on the iron is fixed.
In fact, I don't know the parameters for these items will be important because it's quite yes, so my plan anyway, I want to basically have this and then surrounded by okay, so this is what I want to do. So basically, I just need the classic element, but then this is going to be in my program region anyway, so I'm going to describe this way.
Okay, so you just fix it and then use integration or
and then equilibrate, and then I do the QM, and then I choose.
But again, calibration first, so you go to the QM, like just follow the protocol. Because then if you fix the bonds, just somewhat related to because otherwise the forces are
La única que nos exige es
that's the integration run and do everything.
Casualmente, ¿no?
Integration because then for these bonds
Yeah,
but for these bonds you are busy.
so for so I can use that. But then, for example, this I define it. So I don't define it as one iron 300. Kind of define it as a whole
Depends, no, because then you're starting, no, you should define it separately, because then you're of course rating.
But I just do, so I just define the bonds then, or?
Really, they will probably stick together because of electrostatics, but if you notice, like, you can just parameterize everything, or set up the force field for all the compounds, and then just look how it evolves. If you see, like, okay, they diffuse out of each other because of the environment, then fix it. But you want to go to the other system.
Yeah.
Yeah, so why don't you start straight away from that?
Yeah, that's what was my question.
If you go to run a QM simulation, you will need a good parameter for that. Yeah, not in their formalism, but they
So I
have.
just need something to equilibrate and then.
I would set the charges just to have a good distribution
I
of zone around.
have the charges already for salicylic acid.
But what I was thinking, like, in my group we have developed a method to derive charges in a much more efficient way and a much more realistic way than the rest they're doing. Yeah, like this benchmark study and the rest is actually not good. So I don't know why everyone is sticking to this. It's probably because it's not implemented in most of these programs.
So it must depend on the system a lot because
No, it's not. Yeah, it is, but like in general, they've done a benchmark on a lot of molecules. The method they developed was like always the best. You have Hirschfeld, you have Hirschfeld iterative Hirschfeld. So Hirschfeld is quite bad. Risk is comparable. Yeah, but it's not on the. You have like this Pareto surface or this Pareto efficiency curve, and risk is doing worse as iterative iterative procedure, and then if you have then the iterative stockholder. And then you have a minimal basis iterative stockholder. A minimal basis iterative stockholder is actually perfect for organic molecules. I'm not sure yet how it would work in proteins, as you are also working with these metal ions, or non-metal ions, just have a fixed charge. But it's not probably because it's not implemented in this. Anyway, at the moment when I parameterize my compounds, I started using these charges which come out of the.
Then there's this.
I don't know.
Is there any available software to compute that?
Yeah.
Like a web page, I guess, or something like that.
This is
called.
this is kind of
It's a package from our group. You can also find the paper, and they have quite solid proof that quite solid proof that it's legal.
So the average,
especially if you just use
because
the minimal basis principle works for like the of course, if you start with metals and so on, most of the things
you have like lower than
yeah, so you do just
I don't usually work with organic molecules, but if I have to
with this
it's
correct.
yes, at least for the organic plastics we're working with, when they started simulating them, they benchmarked the atomic charges with different methods and using a CPD simulation. They were trying to reduce the cluster diet, cluster water, and the social functions.
I use for all my stuff. I use this one, the stage. It's kind of a high fructose workflow to compute the salvation period for energy conservation of molecules with bromine. And there you start also with the science ring. In your stage you get the structure from it. And then you can use it coupled with garlics. It's also according to QM code. And then I compute the free loop PCM charges. So PCM is the implicit solvent model. And then I have quantum charges within implicit solvent. So they're really quite nice. Yeah, and then you project it with the rest. You put them in the chargers. This works quite fine, and they're really nice, like good chargers. This is how I usually determine my first atomic charge.
These things usually work.
That's why this is still all these cool efforts. We have all five extra tests.
But for example, even in this phenomenon, when in your region there are some metals like gold, is it okay?
Because it's when I'm talking about metal, I mean I don't mean metallic. About
like you mean metals, not like single atoms.
it's actually the density state.
Okay.
You have a density state. If you have a single ion, there's a band gap. That's it. The smaller band gap, the more problems that you get.
But are there pseudopotentials for these members?
It's just anyways the same in Car-Parrinello both you need well, CPDK and even they you kind of approach it. You can go there, you need to have two systems. So there are some elements which are very difficult. The easiest elements look like the right-hand side of the period table and the transition metals. Less problems with that. Actually, that's it's not only the civilizations, so
And you said someday that these ultrasoft are not good. So now
there's only one type of potential simultaneity. CPD only part of the algorithms that can use it. You can be dynamic at the same time.
But is it worth it? Because your behavior is like 10, so you know something more.
Yeah, so it's Mauro says
in cutoff some sort of?
you can reduce cutoffs to some extent, but we will need another implementation to reduce it more. And then normally it can be immediate. We could reduce more with some more implementation. And then now implementation terms, they are quite heavy. So they cost they part of the Atlantic flow and you need less energy. Less these extra terms they take some time. And then in the advantages depends. The advantage would be that they are for example much more accurate. So you can have several projectors and the same load. So I would like to have an option. Basic dynamics is there, but for DFT,
so only with not and not. Okay, thank you.
I have a last short question. Can you comment on this U and M? So U is the mass and M is the mass of the ions. Okay.
Like now,
the problem with you suggestion is that and usually they ask us really tough.
So the ion has to
I think we were also potential
slowest ion has to be faster than the
myself the way you know that.
Electrons
Then it was really clever.
they oscillate.
That's an answer to my question.
The idea was
We didn't say it, but it was a good answer, no?
so
I was thinking what
kind of average.
In you have to students and then like probably that with them I might ask you the average U3 ask me before that I can really know because I'm really asking something I'm like yeah tough and then I can't because no I don't remember
Some of them are
but at the end
this was the surface with the Car-Parrinello with someone here. We stay more or less but now then on the average we are flowing yeah, initially it was very easy. You slow down, you start to change the energy. If you put it very light, you have very light electrons, then you have to reduce
exactly. So even if we don't tell me we have to try really good at that. And it's like
fast, too fast.
and how different is the system? How I
I can't get think if I'm touching the thing.
First we had to do a couple of tests.
Yeah.
And you look at the concept.
But I'm gonna do it the same. I'm gonna do
For example, your electrons heat up.
so the kind of drift
I wanna
Yeah, and you can think that if they would get too light or too heavy, you can what happens to the atoms. And if you look at the electrons density data, you see the then better put the so the thermal because it's more current. So it's one reason why people suffer and will be. And you use it if you use simple if you say
Thank you.
Però questa parte che c'è un NFA.
ok.
Poi quello lì entra nella
You know, this is something I don't get. So that doesn't make sense to you, then I will explain you. Victor has two sheets. Yeah, I will explain you. Victor has because there's something that I don't have to do. One fix in the other one you do this right here. So this is like the blended gems. And just you have back to consider one. So he has fighting with
Quindi
this
in realtà serve il volume
and this is
totale.
lamps, that is using lamps. And then I asked him something. This is interlayer, different yes, right?
Sì.
But what is lamps for different colors?
The what? Exactly. The different colors with the color of the images. So you can but one thing I was asking him is like one thing I actually
Con questo metodo qua, mettendoci dentro i raggi,
it should be a point at which the
se ci metti le barra, tu hai fatto, hai messo le barra, che devono dire con questo metodo qua che non ecco, cosa molto
This is just to gradually lift
exactly.
No, metti la cella,
Exactly.
bigger gap than here.
e scrivi nel commento che in questa cella prendere e questo numero di particelle corrisponde.
Yeah, okay. But then it means this really should go out. Because I told him I did the same test even with DFT.
Parting fraction.
And then this would have done it.
Poi magari aggiungi queste 3-4 righe qua di come commento
for year of flow. And I get this. And this needs to
sì, però non cambiarla, non cambiare tanto
Yeah, but this is
displacement.
It's not supposed to hands.
No, I think this is. I don't know what it is. I'm not sure. I think it's the percentage of the. I don't know. But anyway, I
see.
Yeah.
With the numbers you gave.
For him, it's still here. If you consider his figure to be described,
Like
your
this.
figure
Like,
to be
like this, right?
Yeah.
Does anything that makes sense for me?
Perché nella versione vecchia, no? Non c'è nella versione nuova.
But I think it's just doing these points. I'm asking.
Sì.
I don't know, he didn't tell me. He just told me these are the displacements. So I told him, figure out what it is.
Sì, le sfere sono...
But anyway, is there anything that people say? Yeah, I think it was 0.5. Yeah, 4? I don't get it.
Allora,
No.
The same?
quindi devo andare in friction. Glass Israel. Ah no, sì, friction. 3D cube shear, 001.
Could be that he's only one asking.
Ok. Lo 00.
Yeah, I think it's the percentage of the cell. I think so. I think so, yeah.
Sì.
I think it's I don't think that is fraction recorded.
Aspetta, scusa, il 101 non è il 100, no, prende solo l'ultimo. Prende solo l'ultimo. Cioè sono tutti uguali. 101, 201. No, aspetta. Il 101 è 136, 376. Sono messi in ordine. Guarda che sul file c'è scritto, è stato scritto da due.
Citations. And Ziggy already?
The?
Yi, secretary.
No.
You get the famous secret envelope.
Okay.
Did you your plan when you went to go? It's temporary exercise of Peter.
Io ho 5 minuti.
You don't have to.
Let's see, that will be a much later.
You can leave it.
Let's see.
I have it, I just used it.
Quindi 101.
That's switched to the new name.
Yes, because I want to come back. I heard it's so hot that I don't need so much plants. So the
you just want your volume. Your water just has to fit around it, and you don't want unrealistic things. Parameters, if you use all the parameters from that. So if you use so the gap for the solute is usually be right. That's what I did, and you can do it. So I used the from the F2 force field.
It's
But that's already a good idea. Because it's a pain in the other works to settle water.
So, yeah, that's crazy fast.
a little bit of the density functional theory part of the CP2K code. If nobody has, or if somebody of you have never used it, is a bit different from the CPMD or other codes. And this is because obviously in the QMM simulations, your time is dominated by the density functional theory part, or if you're using other QM part, in general is anyway dominating your simulation time. Just a question, anybody already used CP2K? Okay, so there are some. So all the others never heard about CP2K, or just heard and never used it? Heard. Okay, good. That's a good, already good base. Okay. So for the history part, CP2K. CP2K was developed or started something like 18 years ago, and it was a joint effort to put together a DFT code and a classical mechanics code. In the history, we had it's an open source code, and we had it first available on this repository site. Then it went to this ForgeNet site, and now it is on the GitHub. So whoever of you was used to download it from the ForgeNet, it's not anymore there. So you can download it from the GitHub. And also development is open, so if you have something to develop for CP2K, you can then make a pull request to the GitHub, and it might be accepted. If it's a good development, it will be accepted. Okay, so that's for where to take it. So it has increased substantially in the past years, both the development and the community of the users. You can find some data about for example, the history of download here, so in the past years, so how many downloads per year. There are also releases, so versions of the code that have been frozen, so and you can access them from the web site of CP2K. It's good that when you make some application, you always use the same release, and when you refer to your papers, you give the reference to the release. Otherwise, there is the trunk version that is the one that it is the development version, and you can also download and use that one. It is a Fortran-based code, but it is the development tries to be modular, so object-oriented. It relies on libraries more and more, I would say. Obviously, the mathematical libraries are most of the codes you use. But there are also now these libraries for sparse algebra that have been developed together with CP2K, but now have been split. So there is another repository for these libraries, because the idea is that these libraries can be used also independently, so for other applications. And these are absolutely necessary for CP2K. So when you download CP2K, you actually download also this other library. That is the DBCSR library. And then obviously there are the parallelization libraries, so that typically get from your machine, from the architecture you using. And then there are some not compulsory libraries, but can help a lot in the performance of your simulation. Okay, this libint is compulsory if you want to do hybrid functional calculations, and otherwise as for example, the libx is not compulsory because many exchange correlation functionals are already implemented in the code, but you can use them also from the library. This one would be a diagonalization library. There are other libraries, other plugins, depending on your application. You can decide which ones to take. For the installation, typically, if you use the toolchain that is available together with CP2K, then all the libraries that are needed are also installed, so are downloaded if they are not on the machine and automatically installed. And it is important because then is everything consistent, so that you install libraries and code with the same compilers, with the same, so everything is consistent and should work optimally if you do use the toolchain. Okay, these are code for atomistic simulations, and it has different methods implemented, among them also QMM. Is mainly based on DFT, but now it has a lot of stuff beyond DFT. For example, there are the hybrid functional, but there is MP2, there is RPA, there is GW, soon there will be also beta salpator, depending for the type of applications you want to do. You might want to go beyond. Obviously, the resources that you need computationally are much larger. There are also simpler methods, so there is molecular mechanics, there is tie binding in different forms. Recently there has been new development in the tie binding part, and that might be also very interesting for QMM. So you can use your QM part, doesn't need to be DFT, it can be that tie binding and on the different forms. For sampling methods, there are the usual ones: geometry optimization, molecular dynamics, even Herrenfest dynamic. You heard about CPMD, where in principle you propagate the molecular orbitals. Herrenfest dynamic is something that where also the electrons are propagated. And as for CPMD, you have to use much smaller time steps, but then you can simulate simple excited states, so you can propagate on excited state surfaces. And then there are sampling tools like sampling the potential energy surface, like NEB, so natural elastic band, or sampling the free energy surface, umbrella sampling, or megadynamics. For path integral, the best thing that you can do is probably to use IPy interface with CP2K, but there is a sort of path integral directly inside CP2K. And for property calculation, it is a changing part, so there is a lot of development there. For example, now we have for TDFT new code. And for different type of properties, like also Raman, NMR, or IR, we are also working on the development that you can find on the web page. Okay, so the main goal is to have simulations with good performance. So the development of CP2K is really pushed towards the use on large machines, a large number of processors, and to have very good scaling. So that is always put as a first target. And then you see here, this is not very recent benchmarks, but it is showing how in the years the performance of CP2K has improved for a specific simulation. In this case, it's just liquid water with DFT, and then you see that the scaling is in particular has improved, and that is because of mainly because of the libraries. The development of the sparse algebra here has obviously changed a lot of the performance. Recently, there is a lot of effort in trying to go to the GPU machines, and then also there you can get improvements. Okay. Yeah?
the last slide, the X are the different architectures. C's and
okay, here in this is the number of cores. This is tendentially the same architecture. It's all a Cray machine. Obviously, it has been changed over the years. So we access a machine that is a computational center, and then if they upgrade, then they have different machines. But these are the scaling is the time for an empty step with different number of processors, always for the same system. And then you see that here we have to stop there, so it says that then you have too long timings, and or you don't have enough processors. And then now, okay, now is not now because this is in 2015. Now we can do better, but then it is still scaling a bit up to 400, okay, maybe 300, and now for sure it's better. Then it depends also on the size of the system. 64 molecules is not that big, so if you take a larger system, that you have a better scaling. Yeah.
Have you got any idea what the scale-up is if you go to GPUs, or does it depend on?
There is, now I don't have the slides, there is information, so you can find, there are information, if you can find benchmarks also on the web page, I think. There one has to be really careful because certain part of the codes are GPU enabled, and it depends also on the communication on the same node between the GPU and the processors. There, typically you have to use OpenMP, so that you have more memories and you have less tasks on the same processor. The best application for GPU are something like hybrid functionals, where you have to do a lot of integrals or MP2 on RPA. So again, for DFT, if you do linear scaling DFT, so with huge system, yes. If you are doing a small system, you don't see anything with GPU. Or if you are, depending on the libraries that dominate your calculation. We can discuss this maybe in more details, depending on the application you have in mind. So, what is special in CP2K, or in the DFT part, now I go to the DFT part of CP2K, is the choice of the basis set representation. So, you probably have already discussed this. So, when you have to solve an electronic structure problem, the first thing you have to do is to represent your wave function, your molecular orbitals in some basis functions, and then having this representation, so in this case with some expansion coefficient C, then you can define the matrices that you need, like the overlap matrix. You obviously have to impose some of the orthogonality of the wave functions, or in general you impose it because it's much easier than to work. And you have a density matrix that it is this sum over the coefficients. F here is the occupation number, and you can define the density in terms of this density matrix. Then, if you have this representation in basis functions and in matrices, then you can rewrite your problem, that is the minimization of the Konesham energy functional, in a matrix form. So you have here all matrices, so the kinetic energy matrix, that depends on this coefficient, this T is the kinetic energy matrix, depends on the coefficients, the external potential, if you have pseudo potentials or nuclei potentials, and the Hartree part and the exchange correlation. And in practice, what you have to do to minimize this functional is to solve this equation, these Konesham equations. It is a simple variational problem with constraints because we have imposed that the orbitals have to be orthogonal. Okay, so then this is again very general, then you solve it self-consistently, so you give a first guess, you calculate your Hamiltonian, you do your first optimization step, so you try to find the solution, check if the convergence of the solution, so if the solution has converged, you exit, you finish, otherwise you go on. So with the solution you construct again the Hamiltonian and you iterate. So this is the self-consistent procedure, and then you stop it at a given required tolerance, different from CPND. If you have discussed on CPND, then you don't do any SCF. Here you always have this iteration, that means several steps of calculating the Hamiltonian, the density, and all the ingredients you need. And you never go to exact convergence. You have always, this you have to remember, you have always the error given by your SCF tolerance. Okay? And that is an error that you cannot avoid, and that, as Ari mentioned, will always then in MD cause a drift. So in a MD based on SCF iteration, you will always have the drift. How much important this drift is left to you, so you have to decide if it is acceptable or not. Okay, so which are the critical tasks in all this? Is to construct the Hamiltonian, calculate the Hartree potential in DFT and the Hartree term, and solve the Kohn-Sham equation, so do the iteration, so from the Hamiltonian get the new molecular orbitals. So these are the bottlenecks, and the idea is to make it as linear scaling as possible. And in this respect, okay, this is what the as linear scaling as possible. And in this respect, the thing that the ingredients we can use, so that we can change in order to improve the performance, is often the choice of the basis set. If you have a plane wave code, it will be the cutoff of your plane wave. In CP2K, it is a bit different because we don't rely on plane waves, or we don't rely only on plane waves. Actually, the method here, that it is the most used method in CP2K for DFT calculation, so the GPW method, is based on the expansion of the molecular orbitals in Gaussian type orbitals, and plane waves are used only as an auxiliary basis set. And I'll try to give an idea of how this is done. So the Gaussian type orbitals are basically some primitive Gaussians that are characterized by exponents here, this alpha, and by the L quantum number. So it can be S functions, P functions, D functions, and so on. The other thing that with GPW is done is to use pseudo-potentials in order to reduce the number of electrons and also reduce the number of basis functions that you need, because if you have to describe all the electrons with this function, you need many functions with also very large exponents, because you want to describe electrons that are very close, really compact around the nucleus, so you need very steep Gaussians, so you want to avoid this, and then you use pseudo-potentials. And the plane waves auxiliary basis set is mainly used for the Hartree part, so for describing the Hartree potentials, because then we can avoid to calculate for electron integrals or for center integrals. Yeah, so this is done exploiting regular grids, where one can describe the density and then fast Fourier transform to bring the density from a real space representation to a reciprocal space representation, so using the plane waves. On the other hand, we use a lot of sparse matrix algebra for everything that is related to the Gaussian calculation. So whenever we do calculation based on the Gaussian representation or the atomic basis function representation, then we can use sparse algebra, because they are very compact and they do not overlap too much. This will allow for very efficient screening. So we can reduce a lot the number of operations that we have to do by these tricks. Let's try to see it a bit more in detail. So about the sparse representation, if we have a Gaussian representation and we have to calculate typically integrals that can be overlap integrals or integrals for terms that are related to specific operators, so for example the kinetic energy integrals, then we have to calculate integrals between Gaussians. If the Gaussians are far apart, they decay within a given range or distance. If they do not overlap, then the integral will be 0. And if you imagine here that this matrix is an operator matrix and the black dots are the elements where this integral is different from 0, you see that for a large enough system, this matrix is number of Gaussian functions times number of Gaussian functions. For many pairs of Gaussian functions, these integrals are 0. So this matrix then is very, very sparse. If we have to do operations, whatever operation with this matrix, we can exploit tricks that are related to the sparse algebra. And that is strongly done in CP2K. And this also, if we know that two Gaussians are far away, we don't try to calculate an integral that we know that will become 0. So based on the distance between the two Gaussian and their amplitude, so how broad they are, we can already from the beginning decide I do not calculate this integral. So we reduce by far the number of operations that we need to do. So this is the screening. And this makes the calculation linear scaling, because we are the number of integrals that we have to calculate increases linearly with the number of atoms that we have. If not, it would increase n squared. Okay? So, okay, the analytic integrals, I don't spend time with Gaussian, they're very easy to calculate. You can use the recursion relation, so this also helps a lot in the calculations or in the implementation of the algorithm. So we have said there are also disadvantages, though. The Gaussian type orbitals are not orthogonal, so we have to use the overlap matrix. So the overlap matrix is not the identity matrix, so we have to deal with that. There might be linear dependencies, and that might make the numerical algorithm unstable. They are typically complicated to generate. One has to optimize basis set based on Gaussians. For the plane waves, you just increase the cutoff, but you don't optimize anything. And often the different basis sets, so different type of basis sets are optimal for different type of methods. So for example, if you use Hartree-Fock instead of DFT, the Gaussian type orbitals that are optimal for Hartree-Fock might be not good for the DFT calculations. If you use MP2, it is again a different type of Gaussian type orbitals that you need. So that might bring difficulties. They are dependent on the atomic position, so when you do MD, you have to consider terms on the forces that depend on your basis function and the position of the basis function. This you don't have with plane waves. These are the Poulet forces that you have to calculate as well. If you forget, or if the developer has forgotten, then you have errors. And there is the basis set superposition error. We will discuss it maybe a bit later. The fact that if you compute with a larger basis set, you have additional terms and you have a better representation, makes a difference, especially when you have two subsystems that come together. So two subsystems that come together are better represented because you have more functions than the two subsystems when they are separated. And that is a problem because then you have lower energies when they are together, just because when they are together they have more functions, not because the interaction energy is stronger. So that you have to take into account. Okay, so this is just a representation or an example of a Gaussian basis set. You see this is all for oxygen. This is for a Gaussian a basis set only for valence electrons, so not for all electrons. So this basis set can be used only with pseudopotentials. So these are here written. Yes, and then in this basis set here, the first one, this is a single zeta valence basis set. You see that there are some numbers up here. So here it says that this basis set is for a function that goes from S, so L quantum number equals 0, to P, L quantum number equals 1. There are 4 functions, so 4 exponents, 1, 2, 3, 4. And you have one contracted Gaussian for S and one contracted Gaussian for P, and these are the contraction coefficients. And the other ones are for larger basis sets. Okay, this is just standard, this is the format that CP2K requires. Okay, these are other functions, but I will go. Just to have an idea, this is all electron basis sets, also oxygen, and then you see the exponent here. Before you had an 8, now you have a 5,000. So that makes a big difference, and this is the reason why we want to avoid it, at least when we work with plane waves. Okay. The basis sets that are available already in CP2K are in the repository in this directory data. Here in red are some file names where there are libraries of basis sets. Obviously, you can generate them yourself, and there are more basis sets that you can find also on the website. Okay. But pseudopotential, I think that you have heard already about it. So it is, as I said, it is used because you want to avoid too often. You want to avoid to describe explicitly the core electrons. I just say about the type of pseudopotential that are mainly used in CP2K. These are the Schodager-Tetherhood pseudopotentials. The advantage of them is that it is analytically represented as Gaussians. So whenever we have to calculate integrals about pseudopotential terms, we still have just to calculate integrals of Gaussians, of products of Gaussians. They are non-conserving. Typically, they need a larger cutoff with respect to other, so plane wave cutoff in this case, with respect to other pseudopotential. But for CP2K, this is not really a problem because the cutoff is never the bottleneck. Very rare. And anyway, it's much more problematic for the exchange and correlation than for the pseudopotential. Yeah, so this, they are typically accurate. This is a potential. Also, in this case, you can always improve. There is development, and optimizing pseudopotential is a bit of an art. And yeah, maybe you want to ask the experts. Good. So then, in our picture with Gaussian type orbitals, in principle you can calculate everything analytically, so the kinetic energy integrals, the external potential integrals, the force center integrals, yeah, but it is expensive. There, as I said, you can try to use GPUs. And for the exchange and correlation part, and in the end for the Hartley part as well, we prefer to use numerical integration. And I'll try to show you how. So the main problem here is the electrostatic potential part, or the electrostatic part. So for the electrostatic part, if you want to do it analytically, you have this force center integrals, and this is very expensive. So we don't want to do that, and so what it is done is to bring the electrostatic potential to the reciprocal space and solve the Poisson equation in G space, and that is much easier. The problem we might have is this representation of density that has been written in terms of expansion of molecular orbitals in Gaussian type orbitals. We have to represent this in reciprocal space. How to do it? So how to have enough accurate representation of the density. Well, first we want the total density because we want also the nuclei density, and we can represent this as well as an expansion in Gaussian functions. And this is the idea. So we have this Gaussian for the nucleus charge here, and this will be the potential represented for determined by this charge. And then, okay, this is the entire part of the electrostatics, so that contains also the nuclear repulsion term and the self-energy term, but these are very easy to calculate, we don't have to care about. Is this one, the term that we have to care about, this integral of the n tot in R times an n tot in R prime. So what we do is to represent this n tot in Gaussians, and to do that we have first to put this n here onto a grid, and then from the grid with fast Fourier transform it into a G-space representation. The problem is to collocate this density on the grid. The accuracy there depends on how fine this grid is. It can be shown that the accuracy improves quite rapidly with the number of points of your grid. And for example, here you see that you have already, for this system is again water. Obviously it depends also on the type of the system, but let's say for water, and so the potentials obviously, with this basis set, that is a triple theta basis set, double polarized, you have already a quite good accuracy. So this is the error of the calculation of the electrostatic part by the representation first on the grid and then fast Fourier transform to the G-space or analytically. And then you see that you have already quite a good accuracy, let's say between 300 and 400 Rydberg of a cutoff for the density. Now, if you compare to a cutoff for CPMD, if I'm not wrong, the cutoff is still given for the wave function, right? Yes. Okay, so that is the cutoff for the density. So if you have an 80 in CPMD, this I think it is about 400 in CP2K. Okay, so not that you get scared. Okay. Okay, so then this is accurate enough. And then this is the procedure, so we get the density represented in Gaussian type orbital, we collocate, we say, the collocation step to put it on the grid. To do this, we collocate already products of Gaussians. You see here it is already the product of the Gaussian nu times the Gaussian nu at the point R big, that it is a grid point. Now we have this sum over all mu nu products, and then we do it, we have it Gaussian, the density of the grid. This sum exploits a lot the screening. So here we collocate only the mu nu that we know that overlap. We collocate them only into a region where we know that they are different from zero. So here a lot of tricks are used to make it fast. Then we use fast Fourier transform to go from the real space grid to the G space, and there we solve the Poisson equation. Okay. We are also, from the grid, we calculate also the gradients. We can calculate of the density, we can calculate it in real space, in G-space, there are different methods. This we need for the exchange and correlation part, because in general you use at least GGA functionals, and then you need at least the gradient of the density. This is done everything on the grids. Also the potential that has been calculated, the Hartley potential that has been calculated in reciprocal space is then back onto the real space grid, and there on the real space grid with numerical integration the total energy or the Hamiltonian or the Kohn-Sham elements are calculated. So with numerical integration on the grid. Okay, so these are the basic ingredients for the GPW scheme. Here you see the GPW functional, and here are highlighted the parts that are done analytically here, based on the this is the density matrix, and the parts that are done instead numerically on the real space grids. Using this scheme, the construction of the Kohn-Sham Hamiltonian, so to arrive to this point here, it is linear scaling. Yeah. There are a few things to consider in order to make everything accurate enough and work fast enough. So one thing is that we said we collocate Gaussians or prototype Gaussians that are still Gaussians on grids. And we want that the grids are good enough, so they are fine enough in order to represent well the Gaussian. But different Gaussians need different grids because they are smooth in a different way, they occupy a different amount of space. The goal here is to represent all the Gaussians with the same number of points, but so to keep an accuracy that is consistent. But if a Gaussian is very broad, I can represent it in over 10 points, let's say, with a quite coarse grid. If a Gaussian is very steep, to have 10 points, I need a very fine grid. So the trick here is to use multi-grids, and according to the Gaussian, decide on which grid I collocate the Gaussian. And so here you see that the broad Gaussian here, the purple Gaussian, is collocated on a grid that is quite large in mesh, and reducing the, so actually increasing the potential, the exponent, it is reduced spacing in the grid. And for this very larger exponent, we use a very fine grid. And then some, the density in the end has to be only on one grid. So then we use interpolation schemes to go, so we have different Gaussians collocated on different grids, but then we need everything on the finest grid. And to do that, we use interpolation schemes. So we have the various contributions on the different grids, and then we interpolate everything on the finest grid that we have. That the finest grid is the grid defined by the cutoff that you put in the input. That will be the finest grid. All the other grids are decided accordingly. The only thing that you can decide is how many grids. Now you can decide on another thing. It is called the relative cutoff, and then maybe I have to spend 2 words about it. The relative cutoff is the cutoff corresponding to the grid where the Gaussian with exponent equal 1 is going to be collocated. This relative cutoff and the largest cutoff that you have, so the cutoff for the finest grid, decides which are the next grids. Obviously also the number of grids. Okay. There are these 3 parameters, number of grids, cutoff and relative cutoff. With these 3 parameters, it is decided which Gaussian goes to which grid. Ideally, you have an homogeneous distribution. You can check it in the output. You want to have more or less the same number of Gaussians for every grid. so that everything is distributed for an optimal performance. Okay. Here it is actually a test on the cutoff for silicon. This is actually the test that you find also in on the exercise or tutorial on the web page. It is a very unfair test because silicon is very easy to converge. So with silicon you get to a wonderful convergence whatever you do. And indeed you have here a wonderful convergence already with relatively small cutoff. Then, I don't know whether you have had a look into the forum of CP2K. It's very frequent the question, well, I tried this convergence with the cutoff and I write to 1000 and still is not converged. Yes, it's absolutely obvious. So you can go nicely to 8000, so to get very fine convergence. Obviously, we are looking here at absolute energies. It's very rare that you need absolute energies. But the other thing is depends a lot on how you do the whole test. First of all, you have to switch off the multigrids. Multigrids are for performance. So you use multigrids in order to make it your calculation faster. But they introduce noise, there is interpolation, there is a lot of stuff in between. So if you want to have an idea of which is the optimal cutoff and get the best convergence that you can, then switch off the multigrids. Then when you found your optimal cutoff, or the cutoff that you can use, then you switch off the multigrid and then you work with the relative cutoff. So at fixed cutoff that you have decided, then you switch on the multigrid and then you decide which is the tolerance in accuracy that you want or you cannot set, working with the relative cutoff and looking for performance. Okay. So, and maybe I mentioned another couple of things to consider about the grids is the fact that we are working for condensed matter, periodic boundary conditions, with systems that should be translational invariant. Now, here, since we are discretizing the representation of the density onto a finite grid, the translational invariance is valid, but for a minimum translation of the grid spacing. Between the grid spacing, since we use interpolation, since there are several other issues in how we calculate the gradients and so on, we have a fluctuation of the energy and also a fluctuation of the forces. So here it is what you see for a helium atom, isolated, in vacuum. If you move it around, the energy should be always the same. There is no interaction, nothing. And instead, if you have a finite grid below, this is not the case. You have this ripple. So you have to deal with this ripple. This is mainly due to the exchange information part. We already do some smoothing, so there are several keywords that you can use to reduce this problem. It's actually not really a problem if you are calculating single point calculation. It can become an issue when you do geometry optimizations. And maybe you're not very much interested in geometry optimization because in MD, who cares? So it's everything very noisy. But for geometry optimization, when you get close to the minimum, then you have always a bit of a movement and the force change. And then you move and the force change. And this is because of this ripple. So for geometry optimization, for example, you might want, if you see that there is some noise, you might want to increase the cutoff. The cutoff reduces the ripple. Or, or you know that there is this issue and you take care of it or you neglect it. But that should be really a noise in the geometry optimization that you see often that for the last part of the geometry optimization it takes forever. And is often due to that.
What is the scale, energy scale?
Yeah, so for the forces, I think it is should be everything. So the energy should be in microartery, and that accordingly. Because I took the graph from another set of slides, and I don't remember exactly. But this cannot be more than microartery, and it should be 10 to the minus 3 in atomic units. It cannot be more than that. But if you require 10 to the minus 4, then you see it. Okay, so now maybe in the very last or two couple of slides, some info about the input, so where to put things here. So, okay, for the basis set, there are in the potentials, there are libraries, and you might want to just give the name of the file or the path to find the file. You can also write them directly in the input at the kind level here. So where you define the kind, here you can, instead of giving the name of the basis set, really write the coefficients of the same for the pseudo potential. Here is the part of the cutoff that we mentioned, so cutoff and relative cutoff. This value here, it is a general value that defines many others. That is a way to define which integrals are considered or not. And there are several values because there is a value for every type of operator, so to say. There are default values in general are good enough, and you can just keep them. If you see that there is problem in convergence or things do not work as you expect, you might want to increase or to reduce actually this tolerance, so say 10 to the minus 12. That means that more integrals are going to be calculated, so you have you are increasing the accuracy. Or let's say like this, less integrals are going to be neglected. Okay, so then we have the functional part. Here you can use the functional that are implemented in CP2K or call the library, the libc library. Other things that are different in this section, so I do not really see. Okay, the kinds here, you see that there are subsections, but maybe this you learn better by the example that are online. Yeah.
So you didn't define how many grids?
It's also here. In mgrid, here is not, but there is a keyword n grids, I think it is, and then they will define the number of grids. Again, in most of the cases, the defaults in CP2K are perfectly reasonable if you're doing water, say, or if you're doing something standard. You can rely on the defaults. But yeah, so that you can try to check.
So if you choose single grid, like single fine grid,
yeah.
It means that you have really large cutoff.
You can, so the cutoff is this one. The cutoff is the one you write in here.
And you choose one grid. So
and this is the finest.
Yes. And then is this you will find the ripple still there?
With the 300, yes.
Okay.
Yeah. So for avoiding the ripples totally, you need for sure a larger cutoff, and here it is. You need some smoothing of the exchange and correlation part. That is already good smoothing. Then again, if you are looking for convergence of the cutoff, switch off the smoothing anyway, because again it is making some not noise, but it's like it is blurring a bit your calculation, so that you get not very fine convergence if you use this grid smoothing, so this exchange correlation smoothing. But then in a normal calculation you might want to use it because then you can use a smaller cutoff. So for a standard calculation. But when you're looking really for convergence, at a very tight convergence, then I will switch it off. and just go for a large cutoff. Yeah, so here it is, so the same thing that we just said. So you look at the cutoff, the relative cutoff, and the number of grids. There are a couple of other keywords. Here it is, wait, here, an example for water. And then you see that now the cutoff has got to 1,600. So that is very different with respect to silicon, and still, if you are looking in these digits here, you still see some change. It's very small. But so we already got the difference between silicon and water. It depends a lot on the exponents that you have in your basis set. We have already seen. You just look at the largest exponent that you have in all your basis functions, and that should be an indicator of which is the cutoff that you have to use. So you can make a correlation between the largest exponent of your basis functions and the cutoff. Okay. The BCC, maybe just this, since it is something different from plane waves, you have to take into account. Obviously, whenever you do calculation or you start for a production run, you have to check the basis function. On some properties you're interested in. So it's it is something that one has to consider. Then when you decide for your basis set, you know that there is always a bit of superposition error, basis set superposition error. For example, if you are calculating cohesion energy, so you have a surface and a molecule, and then you calculate the molecule on the surface, the molecule can profit, so the calculation of the electronic structure of the molecule can profit from the basis functions that are located on the atoms at the surface. When you separate them, because you want to calculate how much energy you gain by putting them together, and then you have the molecule isolated, at that stage the molecule doesn't have the basis function of the surface. You can try to add them artificially, just as basis functions, not atoms. And this is what is done, for example, in the counter correction. Here, so you calculate the molecule, this subsystem A with the basis function of A and B, only the basis function of B, not also the B subsystem. Then you calculate the subsystem B with its basis function of A and B, and then you compare to the calculation of A only with its basis function of A to the calculation of B with only the basis function of B. The difference here is the correction that you have to consider, for example, if you are calculating this absorption energy. Here you see for the cohesion energy of a water molecule in a liquid water, this is a distribution because you have in a liquid 64 water molecules, and for each of them it has been calculated a sort of binding energy. And then you see with different basis sets, so here going down we are getting larger basis sets. Obviously, for larger basis sets, this problem is less important because already the basis set itself has enough functions to describe very well the electronic structure of the molecule. So then we reduce this error here by increasing the basis set quality. You also see that by using this lower quality basis set, the interaction energy is stronger. It's exactly the effect that we said before. So we have a stronger interaction energy because the molecule likes better to stay with the other molecules because there are more basis functions to profit of. While if it is already happy enough with its own basis function, then it doesn't need the other molecules. Okay? So that is exactly the
Just a question about the computational effort. How does it grow with the number of Z?
It grows. Yes. I would say the main feature that increase the computational effort is the choice of the basis set. So it is what changed, because we have these matrices that are number of basis functions and number of basis functions that we have to deal with, and so this is the main point. But yeah, so it also scales rather well. With, so if you increase the number of basis functions, but you also increase the number of processors, the scaling is pretty good.
So that means some of the coefficients could be zero regardless the number of the...
That, yeah, so the scaling is always linear. So if you increase, so because this is, say, it's the part where we have to calculate the Cornish matrix, so it is increasing but linearly, but increases. So it is one of the main, so if you look at the profiling of your calculation, then you will see that the main part is in this algebra, this matrix algebra, and that is everything basis sets. So it's not even number of electrons, it's in basis functions. It's much more important. Also, when you reduce, for example, you decide, I don't know, for ruthenium, you can use a pseudo-potential that gives 60 electrons, or another pseudo-potential that gives 8 electrons. Reducing from the 16 electrons to the 8 electrons, obviously, you gain some time, but mainly you gain if you reduce from a triple zeta to a single zeta. There you gain much more. It's the problem. I think that is my time is over for now. So for this thing, yeah. So then I switch to CP2K, the CP2K, so to a QMML. Yes.
Sorry.
No, it's...
This superposition error is not true for plane waves.
No, it's not true. So because the plane wave, if you have vacuum, you anyway have the same number of plane waves. It doesn't change with the number of where are the atoms. Actually, if you want, it is an inefficient plane wave representation, because even if you have a lot of vacuum anyway, you have to fill it. Yeah.
I have a small question regarding to the relative cutoff you mentioned. Is this the one you screen when which you look for when you put the M grids off?
So when you put the M grids off, you don't need the relative cutoff, because everything goes to this unique grid that you have.
In that case, you calculate the cutoff.
And then you can calculate. You then focus on the cutoff itself. Huh? If you switch the N grids off, then all the Gaussian will be collocated on the same grid, and it will be the finest grid that you have.
And then how can you screen for the relative cutoff?
Then if you add the multi-grids, then you have also a relative cutoff that decides which Gaussians go to which grids. So here, depending on the relative cutoff, here you have this number of you have this number of products of Gaussian. All these ones will go to this coarse grid, and they are for exponents that go from 0 to 1. Okay? Then for those that are from exponent from 1 to 3, they will go to this grid, and so on. Okay? So depending on the number of grids that you have, and on the relative cutoff, here this line, this red line is say the exponent 1, and this decides the cutoff of the grid for Gaussians with exponent 1. Okay? And then depending on the number of grids, you have more possibilities. In the end, you try to make it to say homogeneous, so that you don't have grids that remain empty and grids that get all the effort, because this is not.
This will just increase the efficiency of
the multi-grid just increase the efficiency.
So the relative cutoff will also just have an influence on the efficiency, not necessarily on the calculation.
Yeah, it is an efficiency issue. More questions? then I switch to the next bunch of slides. So this second part is focused on the QMM implementation in CP2K. The main things of QMM are really similar, so I will not say too much about that. What is, I think, different from other codes is how the electrostatics is treated. So maybe I focus a little bit more on that. And give a couple of indications about the Okay, so I don't tell you anything about why and how QMM is intended because you've heard enough on it. Obviously, if we want to do QMM, you need to have a code that has both parts, so the molecular mechanics, say the lower accuracy part and the quantum mechanics part. The CP2K code has both included in one single code because CP2K has also the possibility to run simple molecular mechanics simulations. So it's everything in principle already included. You can add your force field and all the features of a molecular mechanics code are there. If you want to do only molecular mechanics, maybe it's not the code to use because it's not focused on that. So there are probably more, for sure, there are more efficient codes to do just force field calculations. The idea of having it inside CP2K is on the purpose of doing QMM simulations. QMM is often used for biosystems. Maybe, I'm not sure, but probably you have seen most of the applications, so you will see most of the application in biosystems, but it's also used for material science. And it might be very interesting to use on material science because often strains on materials, effects of electrostatics have very long range. And you cannot simulate everything at a quantum mechanics level. And in this simulation, here there is defects created by oxygen penetrating a silicon material. And by doing that, oxygen obviously has to break bonds, so there is some chemistry happening. So you cannot probably rely on force fields alone. And what is done here is an adaptive QMM simulation where the QM region changes depending on where the reaction occurs. And here you have 5 different regions, 5 different QM regions that are adapted during the simulation. And this type of things you can also do. It's a bit more complicated to set up how the regions have to move and change depending on the proceeding of the simulation, but something of this type is also possible, and so the material science is also a field where you can use QMM. So you need the MM environment, and this is the typical force field part, and probably you have always seen this type of force field that include some bonding, non-bonding, electrostatics. These are perfectly possible also in CP2K, exactly as you have in other codes. You can even use exactly the same amber files or charm files for the description of the force field. Yeah, so there are also material science force field implemented in CP2K. They, for example, there are the Tersov or sigma split potentials. These are, let's say, multi-body potentials that are mainly for semiconductors. They are very efficient for semiconductors. There is the embedded atom model. This is mainly used for metals. There are some polarizable models, including the core shell model or some dipole force field. So these things are available. There is no has never been implemented the variable charge model. Otherwise, the topology file is standard and nested to construct as usual, and the parameter files, as I said, you can have the parameters inside the input directly, or you have a parameter file from outside. Yeah, here since you need the force field part, you need also a section in the input that is related to the force field. And as I said, you have to specify some topology, the type of topology. So for example, if it is in a PSF file, you say it is a PSF topology. It can in principle also generate a topology by itself, looking at the connectivity. I'm not sure whether it is to be trusted, but in principle it is possible. And then you can have, as I said, parameters also directly in the input in the force field section. Here, for example, there are the charges that are given for the electrostatics. And another important part, if you are doing periodic calculation, is to define the Ewald section. So if you want to use SPME or standard Ewald, so this is in this section here. Also in the subsection. If you have never used CP2K, maybe you are not familiar with this construction of the input file. It's made of sections and subsections, but this is in general easy to understand, also from the examples online. Okay, you can easily run a subtractive type QMMM. That is the simplest way of combining QM and MM schemes. Just calculating the Hull as an MM, then the subsystem with both typologies of description, so with the QM and MM, and use this subtraction way for the total energy. In this case, the QM part is, so the QM calculation is not affected by the MM. So it is like having an isolated QM calculation and accordingly an isolated MM calculation. Subtracting these two terms, subtracting the isolated MM, in principle you avoid the double counting, because here you have calculated everything MM, and then you have a sort of QMM. The QM is not polarized. This is particular for the electrostatics. The electrostatic of the QM has no idea about the electrostatic of the Hull system, so that there is no polarization. It might still be interesting for certain systems, and the way to do it with CP2K is to use the feature of multiple force environments. So you have to specify that you are running a multiple force environment. The force environment will be the number one, is always the one that mixes the various force environment. And then you have another three. So the full MM, the subsystem QM, and the subsystem MM. So then you have a principal force environment, that is the mixing one, where you specify how you mix. This can be used for also many other type of simulation. In this specific case, you want to mix the 2, 3, and 4 in this way, so such that you sum energy and forces with this formula, so x plus y minus z. These are the names of the 3 environments. As I said, you can invent another formula that you like, the exponential of x minus the logarithm of y plus, that if it is meaningful for you, you can do. And then you have here the entire system, okay, and the entire simulation set. And then there are the 3 force environment individually, so the full MM that will have an MM part. Then there will be the DFT one that will have a DFT part, and here you give the coordinates of the subsystem. And then here there is the subsystem MM, where you have obviously the same coordinates for the subsystem. Obviously, in this case, you need a good force field also for the subsystem. Often you have the case where for the QM subsystem, you don't care about finding a good force field. In this case, you need a force field also for the QM subsystem. Okay. This is the simplest way, and then obviously there is the standard QMM way, where there is the total MM, the QM part, and some way to do the QM-MM interaction. So in this case, the QM is affected by the environment that is described by the MM, and you have the usual ingredients. The QM and the MM part, so the way that how you affect the QM by the presence of the MM, needs to have an electrostatic part if there are charges around. Probably needs to have some non-bonded van der Waals type. And there might be a part of the background charge. The background charge depends on the way you separate the QM and the MM. If the two subsystems are partially charged, you need to have a way to treat these charges. This is in general automatically done. Probably you have to specify if the QM part is charged, such that it is considered. Okay, so there might be force fields where you don't have electrostatics, so then we call it mechanical embedding, and this makes life easy because the electrostatic part is generally the most difficult to treat and also the computationally more expensive for what concerns the QMM term. And yeah, so for example, if you have a depth of potential for the silicon and you are doing something with silicon, you don't have electrostatics, so there are no charges. There is only the steps of potential, and then you need probably just to define which are the atoms that are linked, or the QM part that are linked to atoms of the MM part. Here then you define in a section link which is the QM atom and with which MM atom they are linked, and you define the type of link that you want. In this case, it's just a hydrogen cupping method. Yeah, and then you have in your MM part the specification of the potential, and for the DFT part it will work normally with the standard DFT specifics. Okay, so that instead, in the case of a standard system with electrostatics, like in water, I don't know exactly, yeah, it is there is an unbonded term is always the same, so there will be some van der Waals part, and then there will be the electrostatics. And the electrostatic has to care about the interaction between the density of the DFT part and the charges that are in the MM part. And that means that we have to calculate something like this term here, where we have the charges of the MM part interacting with the density of the DFT part. This often creates problems that have been solved in different ways due to the famous spill-out term. So if you have a point charge, this creates a very deep well that attracts electrons, and it is difficult to handle if you just calculate the interaction as written from the QMM, so as written here, from the individual QMM charge, QMM, this is a charge, the MM charge, and the normal density that it is described in a usual way with the density matrix and the products here of the Gaussian functions. So that has been solved in different ways, so try to smoothing this potential well, but it is especially dangerous for those MM charges that are in the region of your QM system. So for these charges, you have to take care somehow to smoothing of the potential in order to avoid the spill-out. In general, what the simplest thing that you can do, you can calculate the potential on this QMM grid. I think that the mouse has stopped a little. Is this working as well? Yes. So you can calculate the density on in the QM box and calculate this term just on the grid of the QM box. The effort, the computational effort, then will be the number of MM charges times the number of points in the QM grid. Often you want to reduce with the computational effort, and then you define a cutoff, and then you look only at the charges that are within this cutoff, and then you have here a reduced number of charges. And in order to avoid the spill out, you try to use some trick to make the potential that otherwise for a point charge will be a very steep potential, something that is smoother close to the charge. And this avoids that the electrons are dragged by these point charges that are nearby. These methods, you have probably already seen, have been proposed several years ago, and they are standard way of doing this. Still, we have this problem that can be solved only partially by making the potential smoother, and then also we want to accelerate the calculation of the electrostatics. So this problem has been solved in CP2K using the Gaussian expansion of the electrostatic potential. And I tried to describe the method. So the idea is that this potential that is generated by the MM charge is in fact expanded in a series of Gaussians plus a rest term here. So this is the potential, so this is smoothed potential, and it is the sum of these Gaussians plus this very smooth rest term. This smooth rest term is very easy to calculate because it is smooth, and then you need very coarse grids in order to describe this if you describe on grids in real space. And these instead are Gaussian functions that we already mentioned are very easy to treat with our Gaussian type orbital implementation of the DFT part. So in the end, okay, this is the part that will be described in G space, but because it is the smooth part, and it will be easy to describe it with very, very few points. So the idea is then to use again the multi-grid scheme in order to compute the effect of the potential of these Gaussians on the grid of the QM system. And what we will have here, depending on the number of Gaussians and how broad they are, we will collocate them on different grids. And we will do the same thing that we did for the DFT part. We will put the different Gaussians on different grids. These are already contribution to the potentials, so we don't have to calculate anything else. And we then interpolate everything on the finest grid. And this is the same grid that we use for the DFT. So we have an additional contribution of the electrostatic potential on this grid that will be summed to the Hartree potential of the DFT, and then everything is calculated together. The features that is required, the feature that is required for these grids is that they are commensurate, and the interpolation is done by cubic splines. Commensurate means that the points belonging to the coarsest grid are also present in the finer grids. Okay, so this is the scheme. But this is a bit more about how this multi-grid is implemented. As I said, the finest grid is your standard QM grid, and choosing this grid in an optimal way, this part of the calculation will take about 60–80% of the time of the QM part. So the DFT part is in general always the bottleneck, but for the QM part. Okay, that is just a series of examples. So if I have a tight or steep Gaussian, then I will use a smooth. So a fine grid, and yeah, this is. And then you see that you don't see, but anyway, the Gaussians that were here were not overlapping to this grid, so they will not be collocated. Then, if I have a less steep Gaussian, then I can use a coarser grid. This is the range of the grid. I don't touch it anymore. Okay. No, but it's not possible. Okay, anyway. It is too fast, you have to be very fast. But okay, it was less points needed. And then for the coarsest grid, we can put the smoothest component. What happens if you do this one? Okay. So this is the whole grid is used for the smoothest Gaussians. And then it should go. There are too many animations. Okay. Maybe this is stopped. Okay. Cool. And then the scaling here is the number of grid points of the coarsest grid. So that is your scaling for this type of calculations. Okay, in the end, we have to have everything on the finest grid, so step by step. We have to interpolate the various contributions. First, so it is done iteratively, so the coarsest grid, the coarsest -1, and then further on, until we get the whole potential to the finest grid. And that's it. Okay? So that is for the electrostatics, and here is the keywords that you need to activate to have this feature. First is the use of this coupling method, so it's called Gauss, and this is the number of Gaussians for each atom, MM atom. The size of the Gaussian is then adapted to a sort of covalent radius of the, or a radius of the specific kind. And for the rest, there's not much, so that is all the rest is all the same. Yeah, in general, maybe I didn't say it, but there will be a cell of the DFT part that is smaller often than the cell of the QM, of the MM part. Okay, so the last part here is about the periodic boundary conditions. So if you want to do periodic calculations, it is also an issue in QMM calculations, how to extend the periodicity for the QM-MM interactions and for the QM-QM interactions. There are several schemes that are commonly used, often simply a cutoff, so you define a volume that you take into account that maybe extends beyond the size of your simulation cell, and you calculate all the interactions within this cutoff. This is a reactive cutoff approach. Other schemes implement some evil summation, in general between the QM and the MM. So a QM will be seeing all the images, or will consider the periodicity in the MM, but there is no QM-QM periodicity. And that periodicity might be important for certain systems, and I'm thinking here mainly for material science. That might be quite important. The problem is always to get some good scaling also with periodicity. The evil scheme you have seen many times is a way to consider the extended range, the long range effects of the electrostatic potential, describing it so with periodic, taking into account the periodic nature. The main problem here is to have both part described well, so the highly fluctuating part at short range and the very long range that is actually smooth and can be easily represented like in a reciprocal space. So the evil scheme is the usual way of separating these two parts, so the long range smooth that goes into reciprocal space, and the short range fluctuating that goes in the real space. So this is the standard way to do the to treat the periodicity of the yeah, sure.
How do you choose the limit between the reciprocal and
yeah,
is there a recipe?
There are recipes. The idea is that the shorter is the real space cutoff, the less smooth, the least smooth is the other part, so you need more K point for the reciprocal part. In the end, yeah, there is also a way to calculate which is the minimum number of operations depending on where you cut the short range. In addition to that, often you don't use the evil as such, but use the SPME that may makes things anyway more efficient. So with the spline interpolation and yeah, and there are recipes, but it is a matter of I think you have to compensate or to equilibrate the two parts, so to make them equally expensive. Yeah, so the idea is now to treat the full system, so including the background charges if you want, periodically. And that means that you need to have the periodicity in the MM part, the periodicity in the QM, so QM part, and also the periodicity QM-MM. And as I said, the MM is simply done with the Siebel or SPME or all the methods are typically implemented for force field, and in general this comes for free. So if you define that the system is periodic, then this is implemented and you have it. For what concerns the QM, also the QM-MM is in general easily implemented. So you treat, in fact, the QM as an isolated system. So the QM itself is not periodic. You use a different way of solving the Poisson equation, but it is not periodic. But then you introduce the interaction with the images of the MM cell. In GEP, so in the Gaussian expansion of the electrostatic potential, this is easily done because this part is only affecting the smooth part of the electrostatic potential coming from the QM-MM interaction. So this will be a part that just goes to the rest. So what we call the rest is not in the Gaussian expansion. So this will be just a term that is introduced here. And it will be represented on the course grids. So these are the usual stuff that is done in real space with the expansion of the Gaussians. And then we will have an additional term here in the rest that it takes into account also the interaction with the images of the MM cells. And this will be very smooth, as I said, and it will not need any particular effort to do. The periodic part is here, so you will have to give some indication on which is the grid where you put this smooth part, how many replica of the MM part you consider, so how many images you consider, and this will be the cutoff of the G-space expansion for this rest part. So it will be done exactly the same way, just you will get the Gaussian's representation of the potential for point charges that are far away, so that they are in the image cells of the MM part. They will be anyway contributing only a very smooth part of the potential. They will be put in this grid here and with this cutoff. Okay, and that is activated by this periodic subsection in the QM-MM part. So this activates the periodicity between QM and MM. Okay, that's okay. Just a summary. What is still missing? I think, yeah, it is this part. So how to activate the periodicity between the QM boxes. In principle, the QM boxes are separated, and if you define a cell of the QM that it is not as large as the MM cell, you cannot simply directly use the DFT way of doing periodic systems. Nothing prevents from using a QM box that it is as large as the MM box. If you do that, it's done. So you have a fully periodic system, and you can use the standard ways of treating periodic system that it is done, used with DFT. Simply you define this box of this size, and then it is periodic. It's periodic in MM, it's periodic in QM, no additional effort is needed. Often it is not very efficient, depending obviously on the system you have. You want to have a QM box that is much smaller than the MM box. But this type of periodicity is not correct. So if I use this box and I activate the periodicity, the standard DFT periodicity, I get a periodicity that is wrong. The interactions here between the charge, the density of this cell and the density of this cell is wrong, then I cannot do that. So the standard way that we use in GPW cannot be activated here. So we want something that really makes the correct periodicity. How to do that? So in CP2K there is the Blöckel scheme that is implemented that is based on multiples. So when you have separated charges, you can describe the electrostatic effects of one charge, one density, to another place that is far away just using the multiple expansion. So you can then have all the electrostatic effects just describing this density through, or the potential generated by this density through a multiple expansion. This is not valid if the two charges or the two density overlap, but if they are well separated, you can do it easily. Then what is done in this scheme is first taking the QM density and describing it as a sum of point charges, such that this sum of point charges, this is a point charge multiplied by again by a Gaussian. So this way of representing this density has to obviously have the same charge, so corresponds to the integral and has to give the same charge, and has to have the same multiple expansion. So I find these coefficients here, this QM, such that this bunch of individual charges described by this combination of Gaussians has the same multiple expansion as the original density. So this is something that I can do optimize during my calculation. So I find these coefficients. It's just a way of making a fit. The fit has to be done on the minimization of the difference in the density, so this has to be 0, and the difference in the electrostatic potential calculated as an expansion in multiples. If I have done this, I can switch on the the periodicity, just cancelling. So I say that this is a periodic system, so I use the standard periodicity of DFT, and then I cancel the contribution of adjacent cells using, so subtracting the potential generated by this multiple expansion, and I add the term that corresponds to the interaction between the cells at the right distance. So I make a first decoupling and then recoupling. So I decouple from the adjacent cell and couple from between cells that are at the right distance. So in fact, so I cancel, I decouple this interaction here, so QM adjacent, and I instead make the coupling between this and this. This all is done using the multiple expansion of the electrostatic potential generated by the density contained in the QM cell. Okay. This is activated, I think it was in the previous slide. Let me see. Here. It is activated by this section, this multiple section here. And it is by default activated if you have periodic. Then you can, there are some keywords here that can be used, but in general it is if you have periodic, I think that the default is to activate this multiple coupling and decoupling of the QM interaction. Okay. So in the end, here there is an example. This is for a material. It is oxygen vacancy defect in quartz, in fact. And here you see there is the vacancy, so the oxygen, the missing oxygen. And when it is charged, this has a quite strong strain effect over a large distance, and so you want to do it in QMM way. And this particular simulation has been done, I think, with 15,000 atoms, where about 200 were QM. The feature that is observed is how the vacancy migrates by changing here this configuration, that this liner is formed at the beginning, is broken. So when it is formed, there is an electron here that it is shared by the two silicon atoms, but then this time it is broken and the charge is carried around in the system by forming this type of defects where you have three coordinated oxygens of this type. And this has been seen, and can be also be identified in experiments with electron spin resonance, that you have the formation of this type of structure because they have a different signal in the electron spin resonance. So that is something that has been simulated with a very large quartz sample, and as I said, about 200 atoms in the QM region. This is the process that has been observed, and this occurs also because of the very long range of the strain that is introduced by creating this vacancy, and it wouldn't be observed without introducing the QM-QM interaction, so periodic interaction. I think that I stop here, and maybe you have questions. No? I think it's time to break. Okay?
Next is up here what we use last days.
To say that we are going now to the break for lunch. So I was going to show now a little bit some input files for human MSCP and UK, but Marcella made a great job now, already showing things, so probably we'll give just a brief explanation this afternoon after lunch. Okay? So we go for lunch now. We will meet again at 2 p.m. Okay? And yeah, we will do the practical exercise again. Yeah, in the room. I think we can be there, and I will project some slides maybe.